Welcome, sir. GK Sahu, sir, can you unmute yourself?
Yeah, thank you, Gopalji. And first of all, I will welcome all the participants. Then I thanks to IIB for inviting really a health monitoring in all the directions. I just heard that in every aspect they are going to cover. So I was thinking something will be repeated, but I found that there is a really all are covering different aspects. So it is a really great effort.
And sir, just to interrupt, on YouTube, we have right now more than 450 viewers are viewing us.
Yes. So let us
Over
say,
to you, sir.
yeah,
Please.
thank you, Gopal. Uh, yes, as you know, health monitoring is very similar to our health of human structures, you can say. So if we compare the structures as a just living element, not non-living, then it is better actually. Just as we are taking care of our health, same thing we have to do with the structures. So I am going to cover need of instrumentation, instrumented bridges in India, preventive measures for good health of bridge, performance parameters and techniques, monitoring stages, results of instrumented bridges, and if there is so many bridges instrumented, how we can monitor all the bridges simultaneously. That is database management for instrumented. Yeah, you see, in a smart home, we are using so many type of sensors, and you can see from any place what is going on in your home. You can see, you can monitor every activities, whether your gas chula is that is on or off, or your AC is on or off. Anything you can monitor from your office or anywhere. Yeah, even in case of waste management, we are using all the sensors and all the management techniques. You can see anything, energy, industry, healthcare, transportation, defense, everything you are having so many sensors. So why not we can monitor our bridges, which is really neglected so far. We have to really come forward for monitoring of health of structures. So I am going to show some bridges which are already instrumented. This instrumentation started actually in 1990. So this is around 30 years. So we are having very good data at this time, 30 year of data. That is the very good one. And this instrumentation started in India after the collapse of Mandi Bridge. In 1986, when Mandi Bridge collapsed, then people thinking why how we can monitor health of structure. So after 2 3 years of thinking, then it was finalized. First bridge in India will be monitored, will be balanced cantilever Ganga Bridge Varanasi. In 1990, in January, Ministry of Road Transport cleared this bridge for instrumentation. And that is the main starting point from where instrumentation started in India in a big way. Then simply supported Mandavi Bridge, Goa, that was started in 1997, 98. Continuous Bridge, Thane Creek, Navi Mumbai, 98, 99. Aroli, Navi Mumbai, 97, 99. Simply supported Yamuna Bridge, New Delhi, 96, 97. Valence Cantilever Jwari Bridge, that is also 98, 99. And Palam Bridge, New Delhi from 2002 to 2008. So these are the sequence. Ganga Bridge, Varanasi, this is the 4-lane bridge, twin cell box girder, cantilever type, 65-meter on both the sides. Yeah, here that instrumentation has been done in the well foundation, pier, and both the arm of the superstructures. Cantilever 65-meter arm, around 27-meter high pier, and 65-meter deep well. Outer dia of well is 13.5-meter. Very huge structure. This is Mandavi Bridge, Goa. It was also instrumented. Navi Mumbai, the Thane Creek, Aroli Bridge, Navi Mumbai, Loknayak Setu, New Delhi. This new carriageway was instrumented. Then Jwari Bridge here, actually, that instrumentation has been done to see the efficacy of the external pre-stitching work. Then this Palam drain, 6-lane, This was also instrumented. Then Signature Bridge, New Delhi. Yes, there is instrumentation. Naini Bridge, Allahabad, also instrumented. Then Chambal, Kota Bridge, Chambal, there also instrumentation work like that. And these are the new bridges which will be instrumented within a year time that will be started. Actually, that Signature Bridge between Okha and Ved Dwarika in Gujarat. All are cable stayed bridges. And this MG Setu bridge, there is new bridges coming in Patna, parallel to that MG Setu, across the Ganga only. Then at Allahabad, that Phapamo bridge. Then in Jharkhand, Bihar border, that Sahibganj to Manihari, that link, there is Ganga crossing there. So that will be instrumented. So within a year, you will find that these bridges will be instrumented. It will take time, 3 to 4 years, due to that construction activities. But good initiative taken by National Highway Authority of India and Ministry of Road Transport and Highways. They are going to instrument all the big bridges. So they have put this 4 at present, but later on also they are going to put all the major bridges. Yeah, some good view of our bridges in India. Earlier we were thinking if we are not having good bridges in India, but now you can see many bridges. Yeah, that Bandravali ceiling. Yeah, Vidyasagar Setu Hooghly, Atal Setu, Jammu and Kashmir. So all these bridges we are having. So these structures are just like our family. If you compare our family with the concrete family, you will find very much similarity. I have shown one slide. This is just as a constituent wise. You can just compare. Then in parts wise also you can compare that leg, that your knee joint you can compare with hinges, show expansion joint with nose, everything is there. There is too much similarity between human structure and our bridges structure, you can say foundation. Yes, just I have given some example. Reinforcement you can compare with bones, and you can see in pre-stress structure you are having the same thing what our bone is doing for our structure, just maintaining our shape. Same thing in case of pre-stressing, this reinforcement is doing. So you can find very similarity. Even say structure number, you can compare with name of a person, unique name. Design and drawings, yes, as in our body, you can compare RNA, DNA. That is the design and drawing. So I will request all the engineers connected with this webinar, please keep all the design and drawing preserved. Make soft copies, dump into the computer, and really preserve this one, because our future generation will use it whenever they want to some repair rehabilitation. For the last 30 or 40 years back, we are not having any record, and that is creating too much problem while we are going to go for a rehabilitation work. So I will request all the participants kindly keep all our design drawing. That is our RNA DNA. Yeah, you can compare with disease also. Say compressive stress, low blood pressure. As soon as compressive stress reaches at the limiting point, just as we collapse in low blood pressure, when our BP, our pressure just 50, less than 50, we are going to collapse. There is no time. Tensile stress, you can compare high blood pressure. Here there is sometimes you can see some cracks on the structure. We can also feel some uneasiness and we can go to doctor. But compressive stress is the just like low blood pressure. In no time, the human body will collapse like that. Yeah, you see blockage of expansion joint. That is blockage of nose or cold. You can feel. So this is the very important. Blockage of drainage spots you can compare. Non-functioning of kidney blood vessels. Corrosion is the cancer. So you will find too much similarity between the human body, and in human body you are going to use so many sensors, so many techniques, that ultrasound, everything. So why not you can use our structures? Yeah, all these techniques we can So health monitoring is nothing, just like our health monitoring. Similar is the structural health monitoring. And pictorially, we can see there will be some sensor, then some data acquisition sensor. It will be transmitted to the main unit, and we can analyze how the deformations, how the uh, various parameters are varying, and we can find out the stage, what is the health status. And these are the six principles which one should remember actually for any project. GM1, I am getting good management. There should be very good manager to manage the project. Good materials, whatever the materials we are using, that should be perfect one. Good mixed design. Good mixed designs means whenever you are go on changing your source material, anything, sand, coarse aggregate, cement, any steel, anything you are going to change, then you have to see your mixed design also. Good manpower. In every stage we require, whether it is RMC plant, whether it is at the construction side, where it is the design side, where it is the from client side. So that good manpower. Good manufacturing technique to expedite the work. We have to use the latest technique and whatever the advantages. Sometimes we have to just uh, see some techniques which will just give us less time. It will give less construction cost. GM6 is the good maintenance. This is the very important, the sixth one, which we all civil engineers are neglecting. We are thinking that once a structure is constructed, it will last for 100 years without any maintenance. That guarantee we are taking. But it is really very bad. If you are not going for GM6, your structure will be collapsed within 20 to 30 years, not in 100 years. So that thing we should really consider. Yeah, you see, just see expansion joints. People are doing like this. Whenever they are doing that top layer work, after every 3 year, 4 years, they are putting one layer and just blocking the expansion joint. And this is just as our blockage of nose. So I will request all the engineers, please clear expansion joints. Otherwise, you close your nose. Here you can see the expansion joint. They are just, if this gap is more, they are putting one more channel there and welding this type of strips. So this should not be done in any case. This expansion gap is just for the structure to breathe, to expand and contract, not for this type of thing. So these two things, I will request all our highway engineers. This is really very small thing, but very big problem for the structures. If you close your nose, you can feel how much stresses you are feeling. You can see this is the thing. If you are not maintaining expansion joint, yeah, you will find so many things there. All the soil will go out, and then you will find some failure. And here, that at the point of entry, just you will find 50 meter to 50 centimeter to 75 centimeter, just elevation difference. Yeah, you can see we are not maintaining any pipe. Whether we can not maintain this one, this is our tendency only. We should directly attend this one. Yeah, you should put good pipes and good, yes, rain harvesting we should use. Yeah, you can see this is not the place for forest actually, not for green. Yes, we are having places for these trees in other places. So please remove this type of plantation. Yeah, you can see here we don't bother. Once we construct this structure, then we don't want to try anything to clear, to maintain these structures. So you will find after some times this retaining wall will collapse. You see here, very small thing, drainage spots are missing, and it leads to this type of cracks. You see, not only pierhead, you find here also. So these things we should avoid. Drainage spot. So waterproofing of structure is a must. I will say there should be no interaction of water and structure. That is the main thing. If you want to have your structure 100 years, there should be no interaction between water and structure. So you have to do, for that you have to apply whatever required. This is shown like this one. Yeah, you see our maintenance, how we are maintaining our bearings. We don't bother in this stage also. The next year it will be like that. So if this is the case, how we can expect our structure will work? You see here, it is fully cracked, that bearing pedestal, but nobody bothers. Nobody want to see that also by going downstairs and seeing. You see what is the effect of this? Then you have to replace. There is no other thing, and this is the very big operation, just like our knee joint. That's why I am comparing this bearing with the knee joint. You see, in that manpower, you see there is failure within 1 year, 2 year. You see, this retaining wall is around 150-meter length. So we, that is around 600 meter. Nobody is caring. You can see these two lift, there is no reinforcement is continuing. What they have done, whatever the reinforcement, they bend that one and using as a shuttering support, not as a continuous bar. So this type of supervision is there in some of the construction site. How we can expect your structure will stand there? You see, when we are neglecting during construction, that compaction, yeah, then curing, you will not proper that material, then you will find this type of problem. And then you have to do very big repairing work. So it is better during constructions you have to take care. Yeah, for inspection you need mobile bridge inspection you need. That is the big one. But yeah, but very essential so that we can see everything below the structure. Yes, there is drone, there drone technique is, but that is in developing stage. We will use definitely later on in the bigger way. But at present, at least every state should have this one, at least 5 to 6 units. Yeah, then there should be walkway actually. If you are not having mobile bridge inspection unit, we should insist for walkway, because this is the very good way to inspect any bridge. Yeah, you can see the inspection through mobile bridge inspection. You can go at any part, girder, that bearings, and you can see. Yeah, in night also, because if you are monitoring in city area, we have to monitor from 10 to 6, 10 p.m. in the night and morning 6 a.m. So that is the time. So throughout the country, if you are doing, you have to ready for night work also in case of using that work. Yeah, you can see. Yeah. So sometimes this in situ construction is very difficult and we time consuming also. So you can go for composite construction. Yeah, this PR cap you can see in one go we are casting around 10 to 12 meter. This height is around 25 meter, and in only two lift we are casting. Then that segment construction, this is essential actually, and you can see this type of work. Yeah, you can see uh, this design. Yes, design people has to take care that handling stresses. In sometimes I am finding in several bridges there is so many crack during that erection only, because people are designing for the design load but not for erection load. So this should be taken care by the designer. Yeah, sometimes we are lifting whole the girder, sometimes just lifting one segment of the superstructure, but sometimes we are lifting whole superstructure, that whole girder at a time. So that lifting stresses should be taken care during design actually. Yeah, so these techniques we all know, that segmental technique. If you are not caring during construction and maintenance, then you have to go for the external pre-stressing. You see afterwards how many. Yeah, if you are not monitoring, someday this bridge will collapse definitely. This is not in one day work. Actually, if you see it will start like this. And if you don't care for 3 4 years, it will go like this. So that proper inspection and monitoring is essential. You can avoid this collapse of bridges by putting some sensors, by knowing the health status of the structure. You see, this is only due to negligence. We are not inspecting the bridges, not monitoring the bridges. You can see so many collapses. Simple thing, this scaffolding work, we have to provide some diagonal members also. Generally, in scaffolding, you will find horizontal and vertical members, but diagonal is also essential. And sometimes it is getting collapsed during construction. So, to avoid all these type of things, we have to monitor health status of structures. And you find these are the 8 parameters which we can monitor very easily: stress, temperature, deflection, lateral pressure, tilt, crack width, corrosion, and acceleration. By monitoring these parameters, you can comment about the health status of structures. These parameters are common to all the structures. You can monitor a bridge, you can monitor a building, you can monitor nuclear power structure, you can monitor dam. So if we are talking today for bridge, but it will be applicable to all structures. But for choosing any type of sensors, we have to see all these 4 parameters. Suitability for embedded. Some sensors should be embedded because all the exposed sensors you will find sometimes it is difficult to protect those sensors. So it is better once you put during concreting, then it is preserved. Just in the locker you have keep your ornament. So sensors is embedded in concrete, that is gone in the bank locker. Ruggedness for the on-site handling and installation. You have to see how we are going to use. If you are experimenting in the lab, yes, definitely you will need different type of sensor. If you are using at the site, bridge sites or any structure site, you have to use different type of sensor. Long-term stability, our structure is for 100 years, so we have to see that should be long, having very long stability for 100 years. Degradation of the signal, if you are using that cable type nowadays, we are having wireless type also sensors. So if there is cable type, then that long cable length is not allowed in case of electrical techniques. So other techniques we have to use. So that depends on the how much distance you are going to cover during monitoring. Yeah, this is the strain sensor actually. During constructions, you have to embed the sensors, whatever the direction you want, longitudinal strain, transverse strain, anything. You can form rosette also so that you can monitor different strain in different directions. You can find out the surface strain gauges also. You can also weld in steel structures. So surface mounted type of sensors are there. Embedded sensors are there. You can monitor strain at any. Yeah, after putting all those, you can connect with the data logging system if wire type is. Otherwise, with wireless connections also, you can come with to the data logging system. This is just read out in it. Yeah, this is the whole thing which everyone is doing. Yeah, you see, to find out temperature across the thickness, you have to put several sensors so that at different depth you can find out. So this we have done around 27 years back in the 1993 in the Ganga Bridge, Varanasi. Actually, this pier thickness was this pier thickness is around 120 centimeters. So we wanted to know what is the temperature gradient across this thickness. So there we put sensors. Any thickness you can put some sensors and you can find what is their temperature gradient. Then reflection, yes, you can go for any instrument, simple dumping label to LBDT to that 3D terrestrial laser scanner, anything you can use, but we have to know the deflection. That is the very predominant parameter. Then lateral pressure, we can monitor through that earth pressure cells. We have to just say in case of retaining wall or in case of well foundation, we can monitor these things. Yeah, you can just see here we can put and find out. We can put the pressure cells at different levels and we can find out. This tilt meters, through tilt meter we can find out Nowadays, automatically we can also monitor, putting some tilt sensors there, and you can monitor remotely. Inclinometer during construction, if you want to monitor, say, what is the tilt of the well during sinking operation, you can find out through this inclinometer sensor. You have to just insert this sensor in this case. If you want to monitor, you can go for anything that manual monitoring, microscope, or you can put some cracks gauges and you can monitor automatically. This is corrosion sensor during construction. You can put some corrosion sensor and you can find out what is the rate of corrosion. Rate of corrosion means here change in diameter, ineffective diameter per year. You can find out the unit will be change in effective diameter of the bar per year, because very slow phenomena. Yeah, you can monitor anything with the help of our bridge, that mobile bridge inspection unit. You can go to any part, you can take samples, you can check. So that is there. See, in case of accelerometer, you will find so many types. We started from this much size, and now we are using this type of very small sensor. So earlier, this is uniaxial accelerometer, and nowadays you can find this much size only for triaxial sensors. So that is there. If you want to monitor pre-stressing force, you can go for load cells. This can be put between the end bearing plate and anchor plate, and we can see at any time what is the pre-stressing force. So for instrumentation of a bridge, you have to choose some instrumentation scheme. Then these are the parameters which we can. Yeah, in case of well foundation, we can see at different levels. We can monitor this parameter: lateral soil pressure, hoop and longitudinal descent, tilt of well, corrosion. And these are the monitoring stages. We have to take readings. So before putting any sensors, you have to check whether your sensor is working properly or not. That is the first performance evaluation of sensor. At least 2 to 5% of sensors should be checked. During hardening of concrete, during pre-stressing, after completion of construction, during global responses, during peak summer, peak winter, effect of live load, and long-term. These are the stages. Yeah, you can check your sensor by putting strain gauge here and putting some manual strain, just rotating this arm and putting this movement. The displacement we will find out. So delta L by L will give the applied strain, and you can see your output of the sensor, and you can compare. You can put also in some cylinders inside some strain gauges, and you can find out what is the strain output of that gauge and what is the surface strain, what is the strain that is coming or strain control machine also directly. Temperature is very easy. You have to put in temperature bath and with some standard temperature sensor, and you can just compare. For pressure cells also, we have to put that pressure cell inside a chamber and just go on changing the pressure of the fluid, and you can. So these are the very minor testing that is required before putting any sensor on the structure, so that we can get that confidence whether my sensor is working properly or not, that how much this confidence level. So just see, for temperature sensors, we have put so many sensors, and we find this is the temperature gradient during concreting actually. So here you will find minus that's 58 to 48. So only 10-degree differential temperature. That temperature, if you see, that maximum peak temperature should not exceed 70 degrees centigrade, that is the total provision, and differential temperature should not be more than 20 degrees centigrade. If that is more than 20 centigrade, then there will be micro cracks in the structure during concreting. So at the birth of the concrete, we will weaken the structure by not observing the differential temperature. We have to prevent by any way. This differential temperature should not be more than 20. Otherwise, so many micro cracks will be there in the structure. For temperature monitoring, just for a box girder construction, I have shown so many sensors you can put, and you can monitor any temperature gradient in any components of its slab, wave or deck slab, or in junction, anywhere. Yeah, you just find out. This is the deck slab temperature graph during summer. We have put some sensor in the deck slab in different depth, and this is the variation, daily variation, how temperature varies at the deck slab. You can see. This is during pre-staging, how the deflection changes. So this is for 40-meter box girder, four lane 40-meter box girder, I-tube bridge only. Here you will see that 28 mm upward, hogging up. Whole gutter is hogging up. This is also pre-stressing effect. You can monitor what is the pre-stressing effect on the structure. So after every cable pre-stressing, you can see how the strain changing. This 21 and 210 is location is here actually 210 and 21. How the soffit strain is varies. You can see 300 to 350 microstrain is the variation due to pre-stressing. Yeah, this is just how the strain varies due to diurnal temperature variation in the peak summer. So this is the variation. You can see how if something happened, how this behavior changes. Same sensor 14, 17. These are the sensor at the junction of the wave and deck. Yeah, here you will find there is some rain in the summer only in the next year. In the first year we got this type of same sensor, but next year there was rain. Just you see the behavior. So your sensors are really behaving properly. This shows first is smoothly going, there is no change, no rain. Then after rain, you just see how this curve is changing. Yeah, vibration monitoring you can do putting some accelerometers, then some FFT analyzer, then we can find out this type of spectrum. So that is there. Actually, by other speakers will cover. So I will not touch their area. This is the effect of temperature. You can see this temperature variation, how the simply supported box girder deflection changes -1 to 4.5. So 5.5 is the deflection change in the 40 meter box girder due to temperature. You will find at different places. Mumbai, this is for Dwari Bridge, Goa. This is for balanced cantilever Ganga Bridge. Here 25 to 30 millimeter due to temperature. Yeah, this is due to that design load application actually. How much strain? Design load can only put 60 microstrain here. And after recovery, this is reduced to 8.9. We have seen during pre-stressing, the strain is 300 to 350 microstrain. But after application of design load, you will find only 60 microstrain. So that much reserved strain is there in the structure. So that structure is really designed very, very conservative side. In Jari Bridge, you will find so many cracks in different segments. So that external pre-stressing was done. And we have monitored how this compressive strain and how deflection changes. Yeah, this is the scheme actually very big pre-stressing scheme actually. It took around 2 years to complete that pre-stressing scheme there. So really it is a very big work. That external pre-stressing job is not an easy job. You see this much work we have to do and it is very difficult really. Yeah, we have monitored strain as well as deflection. And deflection you will find only that net effect is only 5 to 7 millimeter. So we can't expect very big deformation change due to external pre-stressing. Only that stress level will change, but deformation you can't see. Yeah, just see due to creep effect and sinkage effect, how within 5 years this bridge was constructed. Ganga Bridge Varanasi completed in 97, and I was just monitoring how the deformation of this cantilever is changing. I found that in the 5 year, 97 to 2002, there was deformation of 100 millimeter. You see, within 5 years after construction, this deformation endpoint was ended. So this creep deformation is the really very big problem for the designer. How much creep will be there, and it is very difficult to maintain this segmental construction and cantilever type because the next arm will come here, and both should be at the same order. Otherwise, it will be very difficult. Yeah, this is just showing that lateral pressure variation from Jane, say this is around 8-year data. So you can see any variation. This is around 5-year data for some bridge. This is for 7-year data, how these are varying. So after putting some sensors in the inside, you can find out. If you can't put any sensor, let us take one deflection measurement at the middle or at the middle point, or the simply supported, for cantilever at the end, and let us record that what is the minimum elevation and what is the maximum elevation 2 3 years. Then just give upper limit and lower limit for that bridge, and just take one set of measurement, and let us see after 20 years that level is same or different. If that is in that limit, so there is no degradation on the structure. Degradation will only come when you will allow that water, air, carbon dioxide, etc. You have to prevent these things, so you can keep your structure well. Yeah, for strain variation also we have to see what is the minimum and maximum, and that within that limit that reading should come. Say if one gauge is working out of 100, then also you can comment, because at the beginning you are having that record what is the minimum and maximum variation of a particular gauge, and in any year you can find out this variation is having all the effect, whatever the seasonal variation, that what is the daily variation, considering all those things this has been put. So taking any set of measurement, one set of measurement, you can comment about the health status of the structure. So that is the beauty. Yeah, if there is so many bridges as instrumented, we can go for database management system, and we can monitor any parameter. You can go for any part, whether pier head, well foundation head, what are the sensor and how these things are varies. So all data can be connected with the database. You can monitor any parameters. So this is the health monitoring overall. I will request all of you, all the bridge authorities, to kindly put some sensors in the bridges, so that at the later on we can say something about the health status of the structure. It's CRI concerned, we are having that mobile bridge instruction in it. We are having bearing test facilities, so we can monitor condition assessment of any structures, say bridge, flyover, anything. Then that you can go for the quality assurance also. So these are our activities which we are monitoring there. I thanks to all of you for kind listening. Now I welcome you in question answer session. Okay, Gopal, thanks.
Thank you very much, Engineer J.K. Sahu, sir. Really, it is like from the what will happen if we are not monitoring from that status to how to monitor and what is the importance of monitoring. I think you have given a well beginning. I will take one quick comment or some opinion from our President Engineer Vinay Gupta ji, and then I will go to the second speaker.
Well, I must say it was definitely very interesting to hear Mr. Sahu, and all the information that he has provided is certainly very useful. But I must say that leaving railways aside, in the other sectors, we do lack in our monitoring.
Yeah.
We construct and forget. That is
Yeah,
that, except for railways, of course. With due regards to Mr. Ravind Kumar, Ms. R.K. Goyal. So, all these techniques, everything is known, not known, well documented or not documented. But we must follow. That's very important. What we are doing is in this code that we're making for the cable stayed bridges and extra dose bridges, we are putting something on monitoring, giving details of what all it is. But we are also giving that look, you have to follow this frequency, and at this frequency, what all tests must be done. In fact, Dr. Lakshmi from CRI only is majorly working on it, and that is very important. We know the techniques, but we don't utilize. We don't have a mandate to utilize the techniques.
yeah, that is the problem, sir.
Yes.
Thank you, sir,
We have it. Yeah.
for your comment. Like we'll take few comments after few speakers also, because short of time, we are taking comments of every speaker from the panelist side. Now I invite Professor Sanjay Chikarmane.
Thank
I
you.
request.
Thank you, everyone.
Yeah, thank you, Engineer J.K. Sahu, sir. The attendees can post the questions and we'll take it after all the speaker speak. So you can post your question for J.K. Sahu, sir, in the question box. Over to you, Professor Sanjay Chikarmani. You can say hello so I can confirm your voice.
Hi, how are you?
Yeah, I'm fine. Good. Over to you, Sanjay. Professor Sanjay.
Yeah, so can you see my screen?
Yeah, I can see your screen. The voice is good.
Yeah. So I'm going to be talking on the structural health monitoring of railway bridges. And I'm going to, Sau sir has talked a lot about NHAI. And I'm going to have this presentation limited to railways because that's actually the domain of experience that we have got. We have monitored over, I think, 36 or 37 major bridges in Indian Railways and done several cycles on them. So we have got we've got about 120 data sets of recording. And that's a huge amount of data to actually have or go through a process. And a lot of the things that I'm talking about here are just uh, outcomes which have come from doing this monitoring. Now, fundamentally, what happens is that we believe that structural health monitoring works, and it's nice, and instrumentation is good. And
Professor Sanjay, I'm
yeah,
sorry. Can you full screen your presentation?
oh, of course. Is that better?
Yeah, it is better. Thank you.
Okay. Uh, we of course believe that health monitoring works and instrumentation is good, and that you can monitor a bridge and get data and get some relevant information out of it. And in principle, that's right. And I'm also going to be showing what are the problems in health monitoring as a part of this presentation also. So the background of the presentation is that what is the background and philosophical approach, what are the system identification techniques, what are model updating paradigms, load estimations, damage detections with and without baseline models, applications on PSC girders, and summaries and conclusions. So there are several important bridges in the railway infrastructure, most of which are over 50 years old, and several are more than a century old, but they're still running. And not only are they running, but the loads which are being run on them right now are tremendously more than what they were designed for at the time that they were there, both in the frequency of trains and individual axle loads. Railway had gone from CC to CC plus 6 to CC plus 8 to CC plus 8 plus 2, and now they're talking about 25 tons and HML. And the axle load has gone up from 20 tons to 32 tons, which is huge in the sense that if you're looking at a bridge which was designed for a 20-ton axle load, and now we are saying that we are running 32-ton trains on it, that's a massive, massive change. And the bridges in Indian Railway typically perform well because a lot of the older bridges which were made have been made with a very, very conservative approach of design. And I think that's one thing that we take back from all our assessment of bridges, that having conservative design approaches, while maybe uneconomical in the short run, ends up having your structures which last a long time because your load patterns change, your requirements from them change. And having a conservative approach gives you a certain kind of a way of dealing with change over a period of time. It's critically important to develop a methodology of assessing these structures. And the methodology needs to be robust to ensure that it can be widespread, there's a good acceptance, and that it can be used easily. Now, the hurdles in the path of structural health monitoring, and this is something that a lot of people who are doing structural health monitoring don't talk of, because structural health monitoring, a lot of people end up seeing it as this kind of a magic wand which you can wave at a structure and things are all fine, and that's actually not true. The first is that damage manifests through changes in certain physical parameters. And the identification is not trivial, because very often what happens is that you have got local damage. Okay. And it's easier to monitor global responses. So monitoring a global strain response is relatively easy. But when you are getting a damage at a joint or something like that, what you will be ending up getting is that you'll be getting strain spikes of very local strains, whereas your global strains might not change much. So what you can measure easily may actually not be the feature which is actually sensitive to damage. Parameters are again rarely directly measurable. What we need is that we measure something and then we derive using a lot of signal processing and a lot of physics to find out other parameters. So there's a loss of information at every point of time. It's a structurally inverse problem. And the structurally forward problem is the design problem, that given a set of loads, what is the kind of bridge that you need to make? The inverse problem is that given a set of responses, what is the condition of the bridge? Now, the inverse problem, unfortunately, has a multiple set solution. It is not a single solution problem. And therefore, which is the solution set which actually corresponds to the condition of the bridge and hence the condition of damage is very difficult, really, if not impossible, to come up with in a lot of cases. Uh, when you're going willy-nilly on a bridge, like for example, and I go back to what Dr. Sahu had said, that if you have sensors which you embed at the time of construction of the bridge, what you end up getting is a baseline structure and you get a baseline set of data. Now, changes in the baseline data can indicate damage. Absence of a baseline structure makes it extremely, extremely difficult to identify damage. Now, for example, uh, when you're doing structural health monitoring of a new bridge, you can follow an approach which says that, yeah, we will embed sensors. But a majority of the structures that we have got in the country are not new structures, they're old structures. The deterioration which is typically happening is, again, not so much on new structures, but on older structures. On older structures where the baseline instrumentation has not been done, that's no longer an option. Now, if the baseline instrumentation has not been done, it's not an option. Finding out that what is the baseline structure which is corresponding to this system, and we need to do a model updating. So there is usually a difference between your finite element model that you have made and the way that the bridge actually behaves. And then you have to tune the finite element model in such a way that it kind of starts representing the bridge behavior. And what is the tuning you do is ending up showing you what are the possible kinds of damages which could have happened on this bridge. And that may give you some kind of an indication of what things work like. But in our opinion, even today, structural health monitoring is still in the domain of an art rather than a science. In the sense, it's possible to do it, but you need a lot of experience and a lot of structural wisdom to be able to do it. And therefore, it's not something which can be broken down into a straightforward algorithm as do this, do this, do this, and you'll get that. Problems with model updating, again, it's an inverse problem. Inverse problems are known to be very difficult to deal with. The subsets are created based upon a prima facie structural understanding. You need a lot of global structural wisdom in understanding what are the possible parameters or what are the possible configurations which can correspond to a certain system. It's a multi-parameter, multi-objective optimization, and there is no known procedure for a good global minima. Of course, people have used genetic algorithms, people have used a lot of other things, but absolute global minima is difficult to actually generate. And most optimization is anyway a black box problem. And the physical understanding is rarely addressed when you're doing some of the more advanced optimization techniques. So what has been our approach to the problem? Our approach to the problem has been to develop a physical and engineering understanding of the problem, because at the end of the day, we are engineers. And I don't need a mathematically optimal solution if I can't say what is the physical meaning of that solution. There is a certain, just a minute, I'll just try to get something here. I think that's better now. There's something which you have to generate a premise. And based upon the premise, we have to identify what are the critical parameters which signify deterioration. And we identify critical and sensitive response and generate the instrumentation scheme. Now, this part is, in our opinion, probably one of the most important things which need to be generated, which is that what is it that you're going to monitor? Where is it that you're going to monitor? And what is the duration and what is the frequency with which you're going to monitor? And that is the instrumentation scheme. Now, the instrumentation scheme needs to validate the premise and through this infer some form of a structural condition. And what I'll be doing in this presentation is trying to give maybe a few examples of the things that we have done, and we can take it from there. So this is one of the first bridges that we had taken up. It's a 100-foot span truss girder. It's a very, see, railways follows a very nice principle of having a single design which is replicated through several bridges. So this 100-foot span girder that we have got was a typical RDSO design, which we had come across in at least about 4 or 5 different types of bridges at different places, where the design was the same, which also gave us an understanding, or which also helped us try to figure out that do the same designs behave in the same way in different places. So we came up with an instrumentation scheme. It's a fairly straightforward instrumentation scheme that most of the critical truss members we monitored. The upstream girder we monitored using both top and bottom strain gauges so that you could get an averaging of that as the axial strain and the difference in that as the bending strain. And the other girder we monitored with only axial strain gauges. And this is also one thing, because instrumentation is an expensive process and there has to be a certain optimization of instrumentation which needs to be done. We also had displacement gauges, we had accelerometers, we had thermocouples to measure the temperature, we had tilt meters. So we had done the whole thing. So as far as strain gauges were concerned, we had got the 5mm strain gauges for steel, the longer 120 mm strain gauges for concrete, which we use for measuring both concrete and for masonry. So that was the kind of an instrumentation scheme that we had actually done. We had got the LVDTs to measure the displacements, and we had placed LVDTs at the center of the span, and we had placed LVDTs on the roller side to try and get an inference on what is the fixity at the roller bearing or whether it is completely free. Another bridge that we had managed was a 150-foot span damaged truss girder, where there was a diagonal which was damaged. And this is what, in addition to the instrumentation scheme that we had done for the 100-foot truss girder, we had also done a far more detailed and a far more intensive instrumentation using strain gauges alone for the damaged portion, where we had tried to look at the damaged portion and have several gauges which give you a kind of try to figure out what is the pattern of strain around the damaged portion. We had a similar instrumentation scheme for this. Then we had done a masonry arch, which was a beautiful structure. It is, I think, a 140-year-old masonry arch, which is in Jharkhand. And we had monitored this at the instrumentation scheme was that it was, again, strains and displacements. And we had, of course, done some kind of rail level monitoring to figure out what is the dynamic impact coming on the structure and what are the longitudinal forces being transferred. And, those are the other parameters that we're trying to monitor. System identification techniques, we had several standard methods which we had used. One thing we found out is that global frequencies are insensitive to damage, which is essentially a local phenomena. And although the global frequencies are the easiest to measure, they don't change much. In the sense, whether we looked at a damaged girder or you looked at an undamaged girder. And we had done this in the lab also, where we had created a structure where we had physically introduced damage in the structure. And we had seen that the global frequencies don't change much. Putting a local damage does not really change the global frequencies much. And that is very interesting, because somewhere along the entire thing, there was this expectation that the vibration-based monitoring, that you'd get shifts in global frequencies, which would tell you what the damage is. And now this is very interesting. The global frequencies are the ones which are most easily excited. The local frequencies which correspond to damage have a very low mass participation associated with it, and they're not easy to excite in a structure. So the frequencies which correspond to damage are actually difficult to excite. And the frequencies which are insensitive to damage are easier to excite, and that helps you a lot when you're looking at it from the point of view of how a bridge behaves. but it's not the greatest of things when you're looking at trying to figure out what is the condition of the bridge based upon vibration. In open web girders, we found out that the member frequencies are more sensitive to damage, as the most likely damage is cracks at joints. So this is one thing that we had come up with as a thing, that when we looked at the local frequencies which can come up in members, we found that those are easier to, those are more likely to show damage or to show changes based upon damage. And what we've also figured out is that when you do a spectral decomposition of the bending strain, this can be seen as being analogous to the modal curvature in the beam, which is known as a damage sensitive parameter. So what we found out was that the bending strains and doing a spectral decomposition of the bending strains, and not using accelerometers for frequency measurement, but using the strain data and using the spectral decomposition of the bending strain data, ended up helping us giving us possibly a feature which was more sensitive to damage than the other features that we are looking at. So this was a very nice thing that came up in our research, that we could identify something which was sensitive to damage, because otherwise most things are insensitive. It's nice to say that, yeah, if the structure is damaged, it will behave differently, and it does behave differently, but not in the things that you're measuring. Also, another thing is that what we did is we did several system identification techniques. We did eigenvalue realization, we did stochastic subspace, we did a peak picking, we did a domain decomposition, we did a strain identification with a statistical formulation. These are the types of data that you're using, whether it's ambient acceleration, whether it's free vibration, or it's strain data. And what are the domains? Like some of them are frequency domain techniques, some of them are time domain techniques. And we did all of that put together. And we did, for example, for a 100-foot span steel truss girder, these are the kind of results you're getting. And if you see that the results vary, in the sense it depends, what is the value you get of strain depends upon what method you're using. There is a certain noise in your analysis. So you're not going to be getting the same value no matter what you do. So for example, if you're looking at your mode 1, mode 1 we only got from ERA, so that was good. You got a mode 2 where you got strain, where you got frequencies which had a 5% deviation from each other, and a 5.4% deviation from the numerical model, which was the updated numerical model. And that's interesting, because this 5% deviation is what actually is the range of what damage does. So you have damage within the actual sensitivity of measurement. And if you have damage within the sensitivity of measurement, to say whether it is damaged or whether it is just a sensitivity of measurement is next to impossible. So then what we ended up doing what was a local thing, where we started trying to figure out what were the strain decompositions from the local data. And from there, we ended up picking up different kinds of things. And then you did a thing like, where does it occur? But does it occur in both the girders? Does it occur in only one girder? Does it occur in one and not in the other? Now, in those kinds of things, those kinds of patterns were actually the things which, along with the data, ended up as giving you a damage. So you can already see that damage detection and condition assessment is not a straightforward system, because you ended up needing to do several things, use your engineering knowledge, use your structural wisdom, use different forms of system identification techniques, do different forms of signal processing, and put it all together. And that ended up giving you some kind of an indication. It also ended up as just giving you a trend. And then how do you interpret that trend ends up as becoming more of a structural wisdom kind of a system. So that's actually, in my mind, what condition assessment and damage detection actually is about. We had a summary that time domain methods give several numerical modes. Now, you have to filter out the numerical modes, which is based upon the damping ratios. With you get modes which have negative dampings, which is just a mathematical system. So you say that that's actually a mathematical mode and not really a physical mode. So these are the kind of things that we had to also deal with, that every numerical mode that you're getting is actually not a mode. Whether it is a mode or not depends upon several other things also. And so that's actually the how does one put it? The complexity of condition assessment. Model detection, in most real cases, as baseline undamaged models don't exist. Damaged scenarios need to be checked against numerical models. And then you end up getting some kind of a multi-criteria optimization. And this is a kind of a weighted formula for trying to figure out what is a scalar objective function that you're going to do, which incorporates all the criteria together. And because we can incorporate all the criteria together, it changes the multi-parameter, multi-criteria optimization into something in which a Pareto optimal solution can be actually generated. Issues with the classical techniques is that most optimization techniques work with local minima, which is a black box. We have just talked about this. I'm just repeating a lot in this particular slide. So the approach that we came up with was that we did a two-pass system. That first we did a pass to check the data for consistency. And we had a numerical model which is at least qualitatively representing field data. It might not represent it quantitatively, but it has to qualitatively represent field data for the numerical model to be actually used for doing any kind of an optimization. The multi-criteria are generally taken to be the squared errors to formulate a modified least square approach. And based upon the degree to which a numerical model represents the field, we generated shape norms. And these shape norms, along with the weights, generated what was a Pareto optimal single criteria approach. And then we did a data pass algorithm, which is that multiple runs are recorded, consistency checks are performed to identify shape and peak correlations. And from the various data sets, the best correlated ones are identified for use in model updating exercises. So the model pass algorithm is that you take an n-dimensional solution space and that a start point is taken. And then you do a sensitivity analysis based upon varying parameters. And what we did is based upon the level of sensitivity, we picked the two most sensitive parameters and varied them till we got one solution. And then we picked one parameter out and then took that with the next parameter and then again did a two-pass system. Doing a two-pass system is actually nice because A, it reduces a n-dimensional problem to n-1 two-dimensional problems. And an n-1 two-dimensional problem is computationally far more efficient than an n-dimensional problem. So that's actually the way that we are doing it, because otherwise the n-dimensional problem, we found that it might either you might get a black box solution out of it, which wouldn't tell you much about anything. Or if you wanted a physical solution out of it, the number of iterations would be so high that it would take an exorbitant amount of time in trying to solve it. So these are the ways that we actually started trying to break down our problem and try and see whether we could come up with slightly better results or solutions. So what we talked about, this is the algorithm for that. These are the different procedures that we have got. And these are the different parameters that we had taken, which are the cross-sectional areas. What we ended up saying is that what we were changing were the rotational fixity between elements, which is what we said is signifying damage, because if you've got a riveted plate and there is a damage to a certain rivet, it would change the rotational fixity of that joint. And based upon what is the rotational fixity of that joint, we are trying to see whether there is some kind of a damage at that kind of a place. So if you see, these are the kind of things that we are getting, that this is the variational of the end raker moment over a range, the variation of the rocker side bottom chord over the range. You do a two-parameter sensitivity analysis, and then you're picking up that what is the lowest error, and then you're taking that lowest error and saying that, okay, this means that this is your kind of a fixing of that one parameter, and then you go to the next parameter and then keep doing that. And this is the final values that we ended up as getting. That your boundary fixity, instead of 0 Newton per meter, which means that we started off with assuming ideal roller, you ended up getting a certain fixity because of friction or something, which was 46 meganewton per meter, which isn't really very high, but it's there. You ended up getting a 9% degradation of cross-sectional area of the bottom chord, an 11% degradation of the center area, and about 80 to 85% rotational fixity of all your joints. And this, we said, is indicating that your bridge is in actually quite a good condition, because there isn't much of change really that you're actually getting if you're looking at it from this kind of a perspective of looking at things. And this gives us a kind of a way of looking at a bridge, which shows that the condition of the bridge is okay. Comparisons of secondary responses. So what we did is that the primary response are axial strains for cross girders, for main chord members, and it is bending strains for your rail bearers and cross girders. The secondary responses are bending strains for your main truss members and axial strains for your rail bearers and cross girders. And what we said is that with these parameters and incorporating these levels of parameters, what you're getting is that you're getting a shape correlation between your numerical model and your site data, which is 0.99, 0.95. One means that it is perfectly correlated. So in that sense, what you're getting is that you're getting a very good shape correlation, and you're getting a reasonably good peak correlation factor, because all your peak correlations are within 10% of what your actual site data is. So getting a converged model, which is qualitatively almost 100% and numerically within 10% of your actual site data, is itself a kind of achievement in that sense. And it also ends up showing that because it's possible to have done that, and that the parameters which you changed in order to get your model to correlate exactly with the site data were within the limits of what you expect good conditions of a joint or a member to be, is how you're saying that the condition assessment of the bridge is quite okay. So these are the actual strains, and you're looking at it from the site data, which is blue, the red, which is your numerical updated model, and your green, which is the fundamental numerical model. So here you're actually saying very clearly that what are the differences that happened because of updation. Masonry arch, we did follow the same approach. You took these as your parameter choices and ranges, and you ended up getting correlation factors of this form between the different responses and your numerical responses, between your site recorded data and numerical responses. You did your sensitivity analysis, and you ended up getting what were your final values starting at your relative minima. And you ended up getting an error norm of 0.07, which is a 7% error norm between your site data and your numerical model. And you ended up getting a certain value of your parameters. And the values of these parameters corresponded again to a system which indicates that you have a sound kind of a way of existence. And therefore, this ended up as becoming an assessment which showed that your masonry arch was in a very good condition. And these are the final convergence graphs that we ended up generating. And if you can see that the numerical model and the site data represent each other extremely well throughout the entire domain that we are looking at. And summary, the proposed methods give excellent convergence results for a variety of structures. When problems can be partitioned, they reduce complexity. The approach is seen to outperform the standard solution, and the modeling ideology of the masonry arch coupled with modeling updating algorithm and enables convergence with strain measurements, which is unique. So that was the entire model updating paradigm that we are looking at. Now, this is the way that we have actually approached condition assessment. And I think I've reached about half an hour limit of this talk. So I'm going to stop now and ask that whether there are any questions. I mean, there's more work that we have done, but I just wanted to give a flavor of the kind of work that we have done. So
Yeah, Professor Sanjay, I think we have few questions, but we'll take it during the final course of all the questions we have in the question box. But I will request Engineer Goyal to give his comments towards, because he has told that you have done on the railway bridges. So with us, Engineer Goyal is there.
So I'll
Please,
just
sir.
stop my screen sharing for now. Yeah.
Yeah,
Okay.
yeah.
Thank you, Professor Sanjay Chikarmani.
Hi.
I was expecting this kind of presentation from you because I know you have been deeply involved in design process of open web girder bridges, and you have done a wonderful job, I think, in instrumentation of thermal gradient, that PSC girder near Panvel.
Yes, yes.
So you know all the provisions of Indian Railway codes, and you know the problems also.
Yes.
You know the probable solutions also. So I was really looking forward for a very good presentation from you, and it has been really a wonderful experience for me to listen to you. My request to you is that since you have got the advantage of having a Professor Bridge chair at Roorkee,
That's right.
so that way, any of the IIT, rather, it can be IIT Delhi also, it can be IIT Bombay also, it can be definitely IIT Roorkee is having the advantage that you have got the Professor Bridge chair. So why don't you try to set up a unit specifically for bridge health monitoring of railway bridges at Roorkee?
I
That
think
is
that
a lot of relief to the people, because people are really short of ideas on health monitoring of bridges,
okay.
and you have got that advantage there. So that is my request.
Sure.
Otherwise, everything whatever you have told is wonderful.
Thank you, sir.
Thank you.
Thank you, Professor Chikarmani, and thank you, Engineer.
Just a question. Like the people who ask me questions on the chat, can I just reply to them? Just type an answer and reply back to them?
Yes.
Yeah, you can reply, but once we are open for a question hour, we'll take the question live and you can discuss that time also.
Sure.
Few questions you can reply. If you see that replies, you can do it, you can reply.
Sure. Thank you.
Yeah, thank you, Professor Chikarmani. Now over to one and one, my favorite, Dr. Suresh Bhallaji. Over to you, sir. I think we have covered the basics of health monitoring from Engineer Sahu. Then the all theoretical and analysis, everything. Now Professor Suresh Bhalla will take you us to the in depth to the health monitoring. Professor Dr. Suresh Bhalla, can you unmute yourself?
Yes. Can you hear me?
Yeah, I can hear you. Can you full screen your presentation?
All right. Just give me feedback. Are you able to see it? Are you able to see full screen?
It is fantastic. Good.
Okay, thank you. Just I would like to mention that my home is situated along the runway to IGI. So in some instances, a plane may fly very low. That time I might give a small momentary pause. Okay, so today I am going to present some of the futuristic health monitoring technologies and what path. I'm just pausing. Oh, that was actually, I'm sorry.
Yeah, Professor, we can hear you.
All right. Just a moment. Just a moment.
The slides are not moving, Professor.
I have just lost hold of my slides. Maybe because I gave a pause, small pause. Let me just try buttons. I think I will just stop sharing and I'll just share again.
Correct. Yeah.
Yeah.
Okay.
All right. So basically, I will cover a brief introduction and background, then overview of the current and futuristic technologies, sensors, some practical applications, and the path forward. Basically, what are the opportunities for India and the world? What are the success drivers and need of the hour? So essentially, when we talk in this connection, I don't need to discuss anything. What is the necessity for structural health monitoring? Basically, just like we grow old, we need frequent checkups. So similarly, structures also need this kind of regular health monitoring. The only difference is that we can't wait the structures to get old. We have to start the process right from the beginning, because if we start the monitoring process from beginning, only then we will get the baseline data. Unlike human beings, each structure is unique. So unless we start monitoring them and start understanding their behavior, their responses, and identify the critical parameters, then only we'll be able to make judgment in the future. So we have to start this process quite early, right from the construction stage. And structures hold a number of vulnerable components which are often hidden, and they are slowly affected by different parameters. I mean, different environmental causes like corrosion and many other sort of things. So sometimes this may turn into a sort of catastrophic uh, situation. So we have to have the habit of monitoring the structures. And in this connection, I just want to bring a difference between structural health monitoring and condition assessment. Condition assessment is just one-time establishment of the current conditions, whereas in structural health monitoring, our emphasis is that we should do continuous monitoring. We have to monitor the operating and the loading environment and some critical responses of the structure in a very continuous manner. And similarly, we must distinguish the term structural health monitoring from non-destructive evaluation. Non-destructive evaluation is basically a set of techniques which enable us measurement of some property, physical property, for example, of a material without actually causing any damage. So the NDE techniques, they themselves are not structural health monitoring unless we use them for structural health monitoring in a certain framework such that we are able to get a continuous monitoring data of the structure. Then we say that, of course, this non-destructive evaluation technique is contributing to structural health monitoring. So let's do a quick overview of the current and futuristic technologies and some of the sensors. So we can break down structural health monitoring techniques into global and local. Already speakers have covered examples of both. So global dynamic response techniques are there, global static response techniques are there, and in local, if we apply an ND technique continuously in the framework of structural health monitoring, then that is also fine. And there are in fact specific local monitoring techniques like the electromechanical impedance technique or the EMI technique. We have to judiciously combine global techniques with local techniques because global parameters generally they are not very sensitive to the incipient damage. So as far as the global techniques are concerned, we just try to obtain model or structural parameters by carrying out a dynamic test, or we begin with finite element model and then we do dynamic test and do model updating. So these two versions are there, but essentially most of the techniques, they work in some way or other and look for parameters like change of stiffness, which is obtained from the acquired mode shapes and natural frequencies, or maybe the change in flexibility, again from the model data, or change in curvature, which is nothing but the second derivative of the displacement. So whichever variation one is using, basically we are getting information about the model parameters, and then out of these methods, the damage index method, which basically utilizes the model strain energy, has a definite edge. So the summary is that global dynamic techniques are expedient and they are practical. And out of these, the curvature mode shape and the damage index method, which rely on modal energy, they are having higher sensitivity to damage. But these global techniques, especially the global dynamic techniques, they rely on global modes. So that's why they are sensitive to moderate to severe damage, but they often miss the incipient damage. And we'll see some of the examples how they can be captured. Now, global static techniques, theoretically, they are fine, but they are practically infeasible because they involve applying calculated loads and measuring the deflections or strains, which itself is a difficult task, especially if we have the job of measuring a large number of deflections, then that itself is a troublesome option. However, the global static techniques, they can be used in identifying some operational parameter, like a particular key deflection, key strains at some critical locations. So that way we can definitely make use of them. But capturing damage and its location by standalone measurements could be a bit difficult. And when we talk about SSM sensors, we can classify them as conventional and the new age, the smart material base. Conventional sensors, we have again static and dynamic, and in the smart materials category also we have both static and dynamic type of sensors. So conventional sensors, electrical strain gauges are there, vibrating wire strain gauges are there. Electrical strain gauges, they are suitable for lab based experiments. Vibrating wire strain gauges, they are suitable for field applications. So they are quite versatile, the vibrating wire strain gauges, for long-term strain measurement in the field. And in the dynamic field, essentially the accelerometers, they are most popular. But then the accelerometers, they also face the problem of the small bandwidth, being very expensive and also fragile. So smart material based sensors, they offer new avenues to us. Basically, smart materials are specific materials which possess the property of undergoing specific physical change when subjected to stimulus. That is, they display stimulus response characteristics, and these stimulus response characteristics are utilized to measure the particular parameters. And we have a number of commercial smart materials like optical fibers, shape memory alloys, ER fluids, and piezo materials. So here we'll just briefly discuss about optical fibers and piezo materials. So optical fibers, they are now forming the backbone of the communication systems. They are preferred because they are free from electromagnetic interference as opposed to electrical cabling, and they use the process of total internal reflection for communication. Now they have also entered the field of sensing in the form of fiber Bragg grating sensors and many other type of sensors also. Typically fiber Bragg grating or FBG, in this connection they are quite versatile. Basically FBG is a set of gratings which are imprinted in a small segment of the fiber, and they can reflect a particular wavelength of light. So if we pass a broadband light, what happens is that majority of the signals, they are transmitted to the other end, and one particular wavelength called the Bragg wavelength is reflected back, and this Bragg wavelength is sensitive to any strain, temperature, or pressure changes. So that is the principle used by optical fiber sensors. They are best for static measurements or for low frequency measurements involving health monitoring applications, but they offer multiplexing. So that is very sort of leverage of the optical fibers, that along a single fiber, n number of sensing units can be imprinted, and they can be monitored by just a single channel data logging system. Now, piezo materials, they are smart materials because they show, again, direct and converse effects. Direct effect means that if we apply an alternating say sinusoidal stress signals, what we get is alternating charges, and they are direction dependent. So this feature is used in the sensing applications. So we can utilize this principle to measure strains, dynamic strains, and in the converse effect, essentially, if we apply an alternating electric field, what we see is the development of strain field. So as informed earlier, the direct effect is utilized in sensing applications. Most of the sensors are based on direct effect, and the converse effect is used in actuation applications. So in the structural health monitoring, we in fact use the sensing applications, and in the EMI technique, we use both the sensing and actuation principles together. I'm just halting up. Plane is flying very low, just a couple of seconds. Yeah, now coming to the applications, we are using piezo materials day to day in our life, in igniters, detonators, accelerometers, tactile sensors, pressure transducers, in mobile phones. It's the piezo elements which convert sound signals into electrical signals. Structural health monitoring, energy harvesting. So we'll discuss about energy harvesting also. So basically now in this configuration, the piezo element also acts like a generator. So it's a single unit generator, no moving part. So that way, very compact. The converse effect is utilized again in mobile phones. Now the converse effect is used for converting the electrical pulses into sound in fuel injectors, musical cards, inkjet printers, vibration control, turbo machinery, actuators, precision positioning, and many applications which are so much numerous. Now there are over 200 types of piezo materials, and in the case of the structural health monitoring, basically there is one typical ceramic and one typical polymer which is most widely used. Lead zirconate titanate is most widely used ceramic in structural health monitoring. It has high stiffness, but at the same time it is brittle in nature. Polyvinylidene fluoride, or PVDF, is a very popular polymer. It's ductile, so it's a good sensor, but it has less stiffness, and it also has the advantage that it can conform to any shape. And then there are some special types of piezo materials also. Now, the piezo materials by themselves, they have excellent signal to noise ratio as far as dynamic measurements are concerned. So that's why they definitely have edge over other sensors. And this is a very special type of piezo called as macrofiber compositor, MFC. It can bend, and it's basically made up of piezo-based fibers, so it can affix to even curved surfaces also. And then in our lab, we have made this concrete vibration sensor specifically for concrete structures. This has been transferred to Central Electronics Limited, and this is very rugged for reinforced concrete structures. Typically, here we are comparing the response, the measure dynamic response from the concrete vibration sensor with the accelerometer. So whereas accelerometer is very expensive, the cost of the piezo-based sensors is very nominal. And the best part is that they are manufactured within India. A number of manufacturing companies are there, so which produce these patches indigenously for various applications. Now, when we say technology has future, so when we call future, then it should have some present. So a technique or a sensor qualifies as a futuristic, provided it has at least level 3 or level 4. So basically, technology readiness level has variation from index 1 to 9. 1 means that the system is just in the mind, or it's just at the inception stage, and 9 means that now it's being applied in the field, and in between we have 2 to 8. So if something is there at the initial laboratory test stage, then we definitely know that in the coming years it's going to be a futuristic technique, a futuristic sensor system. So in the case of the piezo patches also, we have some of the operational techniques which are futuristic. Right now they are at the lab stage, and of course they have been applied in site conditions also. We'll just show. So basically, as far as the piezo patches is concerned, basically there are 2 modes. One is dynamic strain sensor, and the other is both the electromechanical impedance sensor using the direct and converse effects together. So we'll discuss each. So basically, in the case of the dynamic strain sensor, it's very simple that this produces voltage, which is directly proportional to the dynamic strain. And the typical sensitivity is roughly of the order of 200 millivolts per microstrain, which is very good for structural engineering applications. And we can use it in a combination as a flexural sensor, that if we have bonding, if we are bonding the piezo sensors, a pair at the top and bottom of a flexury vibrating member, and we use an intelligent combination such that we are getting the voltages together, then this provides as a measure of the curvature. So curvature is something which is regarded as, because it's something related to the flexure rigidity. So here, whereas in the traditional approach, accelerometers are used for experimental model analysis. We can utilize either shaker for lab experiments or hammer for lab experiment. And in the case of the field experiments, we might use the ambient vibration data in the operational mode approach. So here, in fact, instead of utilizing accelerometers, we can use the piezo sensors directly in the way we have just shown, bonding at the top and the bottom. So we obtain the curvature mode shapes directly. The advantage is that the curvature mode higher sensitivity to damage, and they can very easily pinpoint the damage location. The other application is the electromechanical impedance technique. This is also something going to be coming in a large scale in the near future. So here, basically, we first excite the piezo patch bonded to the structure by means of electrical excitation. And in the process, we measure the current flowing through the circuit. The measurement provides us a value of the admittance, the ratio of the measured current to the voltage, and because there is a phase difference, we get real and imaginary components, the conductance and the susceptance. So here the piezo sensor acts as, though we call it as a damage sensor, we call it as a piezo sensor, but in effect, in actuality, it works both as sensor and actuator simultaneously. The technique originally was developed for aerospace structures. Now it is finding applications in civil engineering structures also. So here, typically we use sweep signal, and by this sweep signal, we get measurements at multiple frequencies so that it forms a sort of signature. So what is signature? Signature is just like a thumb impression directly in the frequency domain. It's like a fingerprint. As long as the structure does not have any damage, the signature will have constancy. It will not change. And the moment there is damage, even if it's of the order of an incipient damage, a very minute crack, we would be able to obtain the, we'll be able to capture the damage. Now, sometimes we call these sensors as direct damage sensors because they are measuring data which gives us the damage location and the damage severity directly. But we also call them as stiffness sensors because they can enable, through system identification, the measure of the stiffness of the component, and we have tried it in the case of fatigue. Now, fatigue is something which is very relevant for steel bridges, and is also relevant for low strain fatigue phenomena in the case of concrete bridges. So in the case of the steel components, the technique is very expedient. So we can obtain the direct measure of the stiffness, and then this can be calibrated in the laboratory, and the model can be utilized in the field to obtain a measure of the remaining service life of the structure. I'll just take a pause, and again, an aeroplane is flying very low. Just give me 10 seconds. Okay, sorry for the interruption. Now, this is also very expedient for diagnosing low strain fatigue of reinforced concrete structures. So typically in the form of the CVS, we carried out detailed experimentation, and we could find out the damage location as well as measure of the stiffness and the entire S curve. And these have a lot of potential for real structures. But let me now take you to something connected, which is the energy harvesting. Sensors, if we are bound to build a network of sensors, then sensors, they require power. So the concept of energy harvesting is that we should make an autonomous system so that sensors are able to run on some green power, on something like solar power or the vibrational power. So here piezoelectric energy harvesting relies on vibration power so as to reduce dependence on battery power, so as to highlight the use of green sources and to reduce the costs associated with wiring. And this is very relevant for structural health monitoring and also for the wireless networks, because as the IoT and wireless systems, they are making penetration in the structural health monitoring technology. So the idea of harnessing the vibration energy of the structure, especially the bridges, is gaining ground, and we'll show you some of the real life applications also. So essentially, when we say energy harvesting, so we need a source of external energy, and that is abundant in the vibrations of the bridges. Then we need an element which can convert that vibration into energy, and we have the piezo as the element. We have seen that it can be used as a generator. And then we need to have a conditioning circuit consisting of rectifier and some other circuit elements. And then we need to have the storage unit, say a rechargeable battery, and this can power the load in the form of the sensors. Not only the sensors, it can also enable data processing, data transmission. Now we show some of the practical applications of these techniques. So here we show the monitoring by Professor Ramashankar, MNIT Allahabad. He had been involved in the monitoring of the Neni Bridge, and he used the electromechanical impedance technique, EMI technique, in the bridge. And as the global vibration techniques, they are insensitive to local cracks, so he could very well utilize the EMI technique, and he could notice that whereas in most of the sensors, he had used array of sensors, so he found that the signatures were more or less same, but in one instance, a group of sensors, they were showing abnormally different signatures, and this he could pinpoint the occurrence of a crack, which otherwise most of the other techniques like strain measurement or the global vibration techniques would have missed out. And he could in fact locate with a good amount of accuracy the location of the crack in the Neni Bridge. And this is another application by engineer G.K. Sahu's group, Dr. Naveed. She has demonstrated the measurement of the pre-stressing force using the piezo sensor. So essentially, the principle is that when the element is pre-stressed, then it undergoes change in the frequency, and that shifts the spectra of the signatures. So using that principles, she has demonstrated successful measurement of the pre-stressing force. And now we show you one real-life application of the piezoelectric energy harvesting. This is a bridge just near IIT Delhi across the load. And what you can see here, you see here a cantilever aluminum beam. So this is called as a parasitic structure, and this has a piezo sensor attached at the root. So the idea is that when the bridge undergoes vibrations by the vehicles, so this undergoes vibration, and then strains they develop in the dynamic strains they develop in the piezo sensor, and they can be used for energy harvesting. We'll just show you the video. So here is the close-up picture. So what we have used a magnet to temporarily mount this system on the underside and on the soffit of the girder. And in addition to this, we also bonded directly some of the sensors. These are some of the piezo sensors which we had bonded directly on the underside, and it was a bit difficult. And in some cases, they were broken also, because for curing, we need to press them, and we use a magnet, strong magnet, and sometimes the magnet applied such high pressure that it led to cracking in the piezo sensor. But then we also use the MFC, macrofiber composites. So macrofiber composites, they are much more durable, but then again, the thing is that they are 100 times costlier as compared to bare piezo patches. But we have used both the types of sensors. And here is the this bridge, and I will just start a small video. Just bear with me.
Professor, I think we are not able to.
Yeah, just bear with it and keep watching
Okay.
the video.
Okay.
Now you will see the cantilever vibrating under the loads of vehicles. Now just look carefully. Now here we are charging the capacitor. So I hope the video, it definitely ran, but I'm not sure of the sound, but the sound was not important. I hope you saw the cantilever bridge, the cantilever parasite beam vibrating aluminum. And then you could also see the charging of the capacitor. And in the recent experiment in December, just we were lucky that we did it just before the lockdown. So we could charge a rechargeable battery also. And this is the summary of the results, that we could get power from the directly bonded piezo patches. It was in the microwatt range, and in the case of the secondary structure, the aluminum beam, we could get in the milliwatt range. And this energy is something, this power, what we are measuring is enough to enable structural health monitoring. We checked with a number of commercial sensors, and we could find that this provides enough charging so that we can run these sensors periodically for structural health monitoring. And of course, these techniques also have potential applications in corrosion detection. The electromechanical impedance technique, in fact, in the laboratory model, we have shown that they are quite good in identifying the corrosion stage. And now we just see in the structural health monitoring coming to the end, what is the path forward? So structural health monitoring is still not recognized as a crucial element, and it's not yet part of the codal requirements. And clients are often not fully aware of its benefit and no means of certification. And then above all, there are n number of technologies, and the obsolescence rate is also very high. That causes sometimes confusion to the clients. But then if we see the Indian context, then we can note down some of the success drivers. Basically, those structural health monitoring techniques which are not heavily dependent on modeling, they have a brighter future as compared to others. Then those techniques which require minimal baseline data requirement, or maybe no baseline data requirement, they will have edge. Then in the case of the sensors, those sensors which are usable, which are rugged, which are low cost, and which have long life, certainly they will catch the top position. And the technologies which have cloud and IoT linkage, they will have seen self-powered sensors. They will be something which will go to the top. And of course, integration with the machine learning and AI. Now, the path forward is that the worldwide market for structural health monitoring is bound to grow to at least 6 to 8 billion US dollars. Startups, and it also necessitates continuing education and manpower training, so that the engineers, they have basic knowledge of the structural health monitoring sensors and the techniques. It also calls for the development of low-cost sensors and similar kind of systems, integration of structural health monitoring and energy harvesting, and finally, make in India and made in India. Then it also provides us the opportunities for what our government is emphasizing on being vocal for local. Now, in the case of India, we need trained engineers. We need industry academic joint research. We need an ecosystem for academicians, startups, and industry. And we also need something at the policy level. So in fact, let's see the chart of how the technology grows. So it starts with the physical principles, then it goes to level 3 and 4, that is lab testing and integration with some of the functions in lab, then systems testing, then prototype, then demonstration in operating environment, then certification, and then final adjustment of the system. So this is the stages through which the technologies, Thomas Alva Edison, where a single person could invent so many things. Now, one person cannot invent any single system or single sensor or any device. So it has to be a teamwork of multidisciplinary people. So now coming to the end. So basically, we need very close tie-up between the academic and the industry. We need more R&D projects from the industry. We can sort then industry-driven MTech and PhD projects. We also need speedy invention disclosures, speedy starting of the startups and their encouragement and technology transfers. Now, startup is something that any new thing comes, it's only the startups which drive. Some of these startups, they can succeed, some of them may fail, but that's how the market works. So unless we take the risk, we won't be able to go further in the structural health monitoring dimension. So let me summarize that here we have just seen an overview of the structural health monitoring, some of the technologies and sensors which are right now at the lab stage and which are now going to come in the field. And we have also seen the current status, path forward, and the opportunities for India. So if you want to study more about piezo materials, here we have a book. We have the international edition, and we also have the Indian edition, so which gives complete details of applying these piezo-based sensing right from theory to practice. And you are also most welcome and invited to our virtual lab. The virtual labs, basically there are 100 plus virtual labs right now, and smart structures and dynamics lab is one of them. You can try these experiments. There are two types of experiments, trigger based and the simulation based. So right now, simulation based experiments, they are working. So students who are part of this workshop, they can definitely take part. And here are the references. So again, I thank you very much. You can just follow us in our Facebook pages, SSDL and Futuristic Technologies. Thank you very much.
Thank you, Dr. Professor Suresh Bhallaji. Really, apart from this is the first time apart this concrete aggregate reinforcement. Apart from that, we have heard some new words. Okay, that is the best part. So really, thanks, Professor. We'll take the questions afterwards. I think the all three stalwarts, like they talk about the first part on why the necessity of health monitoring, and then he has shown how the live audit and monitoring has been done. Then Professor Chikarmani has covered the part of important on the railway bridges. Now I will request Dr. Harshvardhan Subbarao to give his opinion towards Dr. Suresh Bhalla's talk.
Very interesting, Professor Bala. That is the most interesting talk. Rarely do we get to know what's happening in the research domain and its implementation in the field. And the success stories. What you're telling us are also success stories and implementable stories for which lessons have to be learned. That is the drawback. The drawback is in communicating the lessons learned to the engineers at large, be it through policy. And I like the overall framework of your entire presentation. It was fabulous, the overall framework. But the policy change, the changes to codes, the ways in which guidelines should be written, it's fine to have a virtual lab to which we can visit and experience some issues. But how do we change this into an adoptable paradigm and move away from this discontinuous, discrete type monitoring to a continuous field of data of monitoring and utilize that data to the benefit of future engineering do's and don'ts and good practices? At the end of the day, what we want from structural health monitoring is lessons learned. I mean, it's like a forensic engineering. There must be something out of it for the benefit of the society of engineers. Otherwise, there's no point doing it. It is fine to say you can assess your design parameters. It's fine to say you can assess your whatever you've assumed in design and damage detection issues and things like that, for whether it's corrosion or cracking or whatever. We're using frag rate sensors, or whether you use piezo systems or what have you. Point is, where do we now stand with the engineering community at large, or is it only left to specialists like you and Dr. Sao and others, and Professor Sao and few others? And railway might have a chair at Roorkee, but general civil engineering and the bridges in India do not have such a chair. So how do we go about creating this change and shifting, doing this paradigm jump to more advanced technologies at a cheaper rate of implementation than the traditional ways in which we are assessing our bridges? That is what we are talking about. I wish you all would throw some more light and bring some focus onto these topics. After all, research done and left on a shelf has no value unless it's implemented. So this is my appeal to you, how to go about forming you appealed we should have academics, policy. You appeal that whole cycle should be there. That is an appeal. What is the way to go about it? I mean, what is DST doing, or how do we do it? Do we need government intervention? Should we set up a society in which we create our own rules like the Chartered Accountants Institute? What is the way to bring about this change which is critically necessary? And where do you get that money to come from? I mean, leaving it to startups is one way, but that is the lowest rung. The larger rung is the framework for all of India for its huge stock of bridges. And you're showing that it can be cheaply done. So why is the resistance to change? These are all the questions that come up, sir. It was the most enjoyable. These are the questions I realized on listening to you. So I'm happy to have been, educated and made aware and bring up these issues for all of us. Thank you, sir. Thank you.
Thank you very much, Dr. Harshvardhan Subbarao, sir. In fact, when I was listening to his presentation, then I thought, like as the trend is there, some shairi should be there. So I have written something. Na bol sakte hain. Think about the bridge. Imagine you are a bridge. Okay. Na bol sakte hain, na shor kar sakte hain. ना बोल सकते हैं ना शोर कर सकते हैं मॉनिटरिंग सेंसर लगा दो पुल में दुर्घटना से बचा सकते हैं तो मतलब this is something we should always remember these sensors save us from the disaster.
Correct.
Now the next speaker, Lieutenant Colonel Harshad Chatty from TPF, the general manager, and engineer Sahil Matre, the director from DGC Engineering Private Limited. I think they will, like all we have listened on the practical and theoretical, but they are sharing one of the live example which they have done. So over to Colonel Harshad, Lieutenant Colonel Harshad Chatty and engineer Sahil Matre. Harshad, can you unmute yourself? Harshad, can you unmute yourself? Harshad, we can't hear you.
Now you can hear me?
Yeah, you can hear. You maximize the presentation.
Yes, I'll do that. I'll do that.
Please.
Can you see my presentation in full mode?
Yes, absolutely.
Okay. Yeah.
First of all, good evening to you all. I'm Colonel Harshad Chatty, and I'll be presenting this work which we have done along with engineer Sahil Mahatre. This work was of carrying out structural health monitoring of Mithi River Bridge on N1 taxiway at Chhatrapati Shivaji Maharaj International Airport. This was done in year 2015 and 16. The slides have been prepared by 21st SHM consultant, which is part of DGC. Coming to I'm showing the aerial view of Chhatrapati Shivaji Maharaj International Airport. You can see a water channel over here. This is Mithi River, and it crosses, the Mithi River crosses the taxiway and a part of the runway. The Mumbai airport has two runways. The main runway is 3,000 meter long, while the secondary runway is 2,500 meter long. Most of the time, it is the main runway which is operational, and the feeder to that is the N1 taxiway. This work was done when in 2015-16, when the this new airport terminal was coming up and it was in final stages. It was operational, but few of the bays were under construction. Now, our bridge site is exactly where the aircraft is standing. So below, this is the Mithi River, and this bridge was on the taxiway. So this is the first time, I think, we have, the eminent speakers before me have talked of vehicle load and rail load. This is the first time where the aircraft load was being tested on the bridge. The access to the site, as you can see from this viewfoil, was not possible from any other side, except we have to bring all these stores, materials from after getting the security clearances. And this was the only opening which was available to access the site. The agencies involved in the projects were MIAL, GVK was the lead contractor, Larsen and Toubro was the executing agency, 21st SHM part of DGC was carrying out the structural instrumentation, and Tandon consultants were the designers as well as were checking the parameters for the bridges. A little bit about the bridge. Bridge across the Mithi River was built way back by Airport Authority of India. The overall width of the bridge was 120 meters. it comprises of 5 parts. The central part was the carriageway, main taxiway basically. Adjacent to them were the shoulders, and thereafter the serviceways. You can see there are 4 expansion joints, while in the drawing it is given old taxiway and old alignment of the runway. The substructure comprised of RCC abutment walls and RCC wall type piers along this line. The box girders were there. There are 60 box girders, and which was divided into the compartment by a diaphragm beams over the piers. The box girders were segmented into 3 with 8 meters at the end and the central portion being of 22 meters. There were openings of 1.5 feet to access either end of the tube at the ends to access the other adjacent tubes. There was phase-wise expansion which has taken place over the bridge. The bridge was strengthened before the right shoulder by R&M International carrying out fiber wrapping in year 2007-8. During this expansion work which was done by L&T, they have casted an additional slab over the bridge and over the deck slab of the original bridge. Now this is the opening which I am talking of, which were there in the diaphragm beams and in the girders where we could access the other tubes. This was the strengthening work which was done by R&M in 2007-8. Now in the month of October 2015, we were called upon by L&T saying that the strengthened portion which we have done has developed, the deck slab has developed cracks. When we visited the site, that time we realized that the strengthened portion had not developed the crack, but the main carriageway had developed the crack. The structural cracks were evident on the deck slab, and you can see over here the rear path of the rear wheel of the aircraft was passing close to the cantilever portion of this expansion joint. Therefore, it was decided these distresses were caused because of the shifting of the center line by 15 meters and the traversing of the rear pathway, rear wheel of the aircraft near the expansion joint. Therefore, it was decided to check whether there are distresses in the girders below 2. So, this was the drawing which was approved by the consultant to have the investigation done for the girders below. Now, in initial phase, it was decided that the conditional survey be carried out near this expansion joint through the openings which were available on the top. As we have to work in the confined spaces, therefore special safety measures were required to be undertaken, like special clothing, helmets, portable oxygen cylinders, because the air inside was doubtful, basically. Torches were required as no other light was there. Walkie-talkie relay systems were installed. Anything happening to a person who is carrying out a conditional survey of the girder over here had to be pulled out through this opening only after crossing the entire stretch. So emergency measures for evacuations were ensured with safety ropes, ambulance inside, and doctor on call. Before starting the conditional survey, fumigations through the open chambers was carried out, such that there are no insects or such things over there. When we carried out the conditional survey of the box, we realized that all the tubes were filled with water and muddy water. These were the openings which I was talking of to access the other adjacent tubes. Now you can see all the mud. I mean, over the period, it was all muddy, the water, and the environmental condition for the structure over there was severe. The survey was carried out using torchlights, and electric halogen lamps were restricted to dry surfaces only. Structural distress cracks were observed, recorded, and noted. It was observed the deck slab has cracked, and through this the water was leaking. This is the same. Crack width was recorded by crack meter, and depth was also recorded. Incidentally, this crack meter was given to me by engineer Gupta Sahab of Tandon Consultants, and I preserve it till date as a souvenir. Now, after the distresses were seen in the girders, thereafter the deliberation was made as to what to do about the thing, whether to go about getting the complete bridge rehabilitation to be done. Then it was arrived at, because that was very costly. That was going to cost a lot of time and also consume a lot of time. So it was decided that we will do the conditional survey for all the girders and carry out the NDT2, and thereafter carry out structural health monitoring by establishing LVDT and strain gauges, and acquire the data with a live aircraft load, such that the parameters, the designers could check the parameters, whether the parameters were in range or not. And thereafter arriving at the percentile deficiency or oblique the strengthening which was required, and also arriving at the best and economic repair method. Now, all this was required to be done in 30 days. This was a challenging task. Now, the planning and execution of the work was done in phases. First was the induction of the complete assembly, access to the site, basically drilling. Since the main taxiway cannot be halted for such a long period, it was decided that octagonal holes will be drilled at the bottom slab, such that the access to the tubes for conditioning survey of the girders can be done. The drawings for the same were given by the consultant. The detailed investigation of the box girders, thereafter CAT mapping, monitoring of the LVDT and strain gauges, and recording of the deflection strain values. Excuse me. Sahil will, the area for the carrying out the structural health monitoring was restricted to the new carriageway, main carriageway, and there around 62 LVDTs and strain gauge points were identified by the consultants where recordings were to be carried out. Now, Sahil will take you further till data acquisition, how he went about mobilizing the site and acquiring the data.
Thank you, Colonel.
Yeah, Colonel, can you mute yourself?
Yes, sir.
Yes, Sahil. Sahil, we need full screen. Yes, I'll go ahead.
There is an echo from Sahil's end, I guess. Gopal.
Acha, echo from Sahil end.
Go ahead. Please, Gopal, please unmute yourself.
Sahil, you can take the place of Colonel and you can present. I think it is very interesting that on Mithi River is a Nala, and in the Nala, if you are doing such monitoring, and this is the, I think at the end you will conclude. Sahil, can you speak? We cannot hear Sahil also, we cannot hear Colonel also.
While they are setting up their sound system or whatever,
yeah,
let me everybody that working at an airport is so very difficult that it makes your life miserable. And the reason is that every minute at the runway has a cost. Aircrafts are doing a minute to minute kind of a job that no time is wasted because you don't have very many extra runways or something like that. So they went to the extent, since we were involved also in some way in this project, they went to the extent of saying the airlines that, look, we will do like this, that in the midnight, you give us some time, we will fly at that time. But the time when you give us to fly, we don't want to utilize the entire time for only getting the aircraft and then flying. We'll keep the aircraft ready. And how to keep the aircraft ready? We will take the aircraft towed through that trailer or tractor, what you have, which pulls the aircraft. We'll use that, bring the aircraft there, and then just fly. As soon as you give us the time, that is to, because there's a block time which is over, we'll start flying. So every minute they have to save. And in those conditions, these people have worked when 30 days was a period given for the huge job of repair. So, Sahil, I hope you are ready now. I don't hear any sound from Sahil.
Sahil, your voice is not. We can't hear you, Sahil.
So it's a big job working at the airport, and then of course strengthening a bridge to the extent of taking aircraft load was another, no less than a wonder.
Yeah, I think there is some.
Sahil is on mute. Sahil, you have to unmute yourself.
Sahil, can you unmute yourself?
Hello.
Sahil, there is an exit the system where Kamil was presenting. That is the reason echo is coming. Ask him to leave the meeting for a time. There won't be any echo.
Sir, आप उधर ही सर. Sir, am I audible?
Yeah, you are audible. You go ahead.
Okay.
Can you make a full screen, Sahil?
Yes, sir.
Good.
Yeah. Sorry for the disturbance. So, thank you, Colonel, for giving me this opportunity to present the future scope of this project. So, so this was the entry to the site, and over here on the left-hand side, you can see there is a small opening from which we transferred all the scaffoldings as well as the instrumentations required to carry out the condition assessment of the bridge. Over here, you can also see a generator which we had hired for 30 days so that we can continuously supply so that we can continuously give the electric supply to the instruments which were mounted below the taxiway. Also, as this was high security area, the whole area it was completely caged. On the right side, you can see an image of the Mithi River. So, as it was a retreating monsoon, the water level in the Mithi River, it had gone up and it was almost above the knee height. So, placing the scaffoldings was very difficult, and because of that, we used to hire laborers. Then the laborers used to visit on site, and by looking at the condition of site, they used to get scared. One second, sir. So once they used to visit on site, they used to get scared, and the next time we used to again hire some other laborers, and then the whole induction process of L&T we had to go through. So overall, we had hired around 90 laborers, and the whole task was to be completed in 30 days, and then 80 to 90 laborers were hired because every day the 10 laborers used to come and then they used to leave. So in this site there were 3 bays, and this was the arrangement we had made to reach the site, all 3 bays, and all the 3 bays were connected with this platform so that we can easily access each and every sensor. On the left hand side, you can see the pathway to the site location, and in the bottom of this screen, you can see we had erected independent platforms for mounting of sensors. The same platforms were erected in all the three bays, so that we can mount the sensors easily. As Colonel had mentioned, we had to drill octagonal holes below the slab. So this was the initial stage, and this was the final stage where the octagonal shape holes were drilled, and all the instruments were transferred from this hole, as well as the individuals carrying oxygen cylinders. They used to go inside this. They used to place halogens over there at the dry platforms, and then we used to mount sensors. Also, as it was required, the non-destructive testing of the girders was carried out. Rebound hammer tests where the rebound hammer test was carried out to find the hardness of the concrete, as well as we had used UPV to find the integrity of the concrete. Now the main part of this whole condition assessment was to record the deflection as well as the strain values. The parameters for the deflection and strain in the concrete were to be obtained, for which we had placed around 62 sensors, 62 LVDTs and 62 strain gauges all across the three bays. The most difficult part of it was wiring. Initially, we had planned that we will take the whole station on above, but then as the wires, the length of the wire, it was like increasing, so, and which will cause a loss in noise, a loss in data, as well as there was a lot of noise coming in the data. So we decided that we will acquire the data in the central bay, so that we can use short wires. So the wiring was done at 62 different locations, and the whole station was in the central bay. As informed, all the heavy aircraft, they used to come late at night, like all the Airbus 380s of Singapore Airlines, then Emirates, they used to come late at night. And we were given the chance to record the deflections and strain values of heavy aircraft. So at around post midnight, we started the whole procedure and to record the flight movement, the nose wheel path as well as the rear wheel path. All the CCTV cameras were installed by taking special permissions from the MIAL. Also, the timings of the nose wheel and the rear wheels are recorded, so that they can be matched with the sensor timings in the data acquisition system. These were the sensors which were used for the instrumentation of the bridge. The strain gauges and the ELAP linear potentiometer. The strain gauges of 60 mm length and resistance of 120 ohms, and the ELAP potentiometer with the least count of 0.01 mm. So as we used LVDT, it is basically used to measure the linear displacement. So by mounting our sensors below the bridge, we calculated the linear displacement. But as it is a non-electrical quantity, it is then converted into electrical quantity via output voltage. It has basically two types of windings. The primary winding in the center, and at the corners, two secondary windings. And it is called differential because it calculates the voltage difference between the two secondary windings. The primary winding is also excited by alternating current source, which produces the electromagnetic field, which also induces the currents in the secondary windings. For data acquisition, we used a National Instrument DAC 9178. So in this DAC, there are 8 slots where we can find out the deflections, as well as we can monitor the strain, and we can find the natural frequency of the bridge. As you can see over here, these are the linear potentiometers which were mounted below the girders. In the center one, it was mounted above the scaffolding, and huge stands were made. So, and also you can see the wire mesh. So basically we used wired sensors because the range below the Miti River, it was not quite great. So, and we had to monitor the real-time data. So all the station we made in the central bay itself. Also on the right side image, you can see the linear potentiometers which were mounted inside the tubes. This is the station which were used for data acquisition below the deck. Here you can see all the wired networks of 62 LVDTs and 62 strain gauges. They were bought in the central bay. And also the main problem working over here was of mosquitoes and different types of insects. And at the wee hours in the night, like around at 2 a.m., 3 a.m., the insects were at the peak. So we continuously had to create a smoke over there. So this was this was the system which we had placed below the girder. Over here you can see the data acquisition system, as well as we had placed a computer over there with high memory, so that all the sensors were recorded for continuous 6 hours. Now I would like to hand over to Colonel Harshad Chatti. He can carry forward in the presentation. Thank you.
Harshad, sorry to interrupt. Your voice is not very clear. Can you close to the speaker or mic? Sahil, can you unmute? Can you unmute yourself? Sahil, can you mute yourself? Sahil. Yeah, Colonel, you can tell. Colonel Harshad. Colonel, we can't hear you anything. We can't hear you, Colonel. Yeah, I think there is an interruption. We need to take, meanwhile, before it starts. Okay, let me request engineer, our Director General, DG Dute sir, to give today's Harshad, can you,
Can you hear me now?
Yeah, we can hear you. Yes, go ahead. Please go ahead.
I'm sorry for this. So as I was, I'll just make this again full screen. Just a minute. Give me a minute, please. Thank you. Yeah, this project was of very high importance, and therefore redundancy had to be built in, and we had to ensure that the data which was captured has to be correlated. Therefore, we had employed 2 NI systems with their softwares, and as it was appreciated by the consultants that the readings will be in mm, so we had to be very accurate. So the strain readings which were obtained for the British, various aircrafts, this testing was carried out for 4 days, 4 nights continuously, such that we acquired data and then we shared with the consultants. And this was the readings which were obtained through one of the NI systems which we inquired. You can see the timings over here and date and timings over here where when the data was acquired. Similarly, the second NI system which we employed, with that also we captured the complete good signals, and practically their readings were in of 2.6 mm. So that with that accuracy we acquired the data in such tough situations. These are some of the views. The top recording was going on with date and timing, such that the data which was collected down below could be correlated with the aircraft. And the aircraft loading was given by the Airport Authority of India to the consultants who had analyzed the bridge, such that their bridge parameters could be ascertained. This was the rear nose wheel path and rear wheel path which was there. So based on our results obtained through the structural health monitoring, it was decided by the consultants that the parameters were in range, and therefore it was recommended that instead of going for a major rehabilitation work, which earlier they were contemplating, only crack filling with low viscosity grout and strengthening of the expansion joint or the cantilever portion of the expansion joint by introducing additional lugs for shear deficiency. This complete exercise resulted in a lot of savings. Now, challenges at site, like Engineer Gupta sir was saying, Mumbai airport handles around 900 to 1,000 flights, and at that point of time, and not as of today in this COVID situation, but at that point of time, it was handling 900 to 1,000 flights per day. Practically, a flight takes off or land at the rate of every 1.5 minutes per minute. And whoever has taken a flight from Mumbai would have experienced that there is extensive waiting period before the takeoff of the aircraft. And this is exactly where the N1 taxiway and our bridge site was. So whenever on a taxiway, the aircraft is there, the norm is you cannot cross the taxiway. So it practically used to happen that we used to go for work at early in the morning, 8 o'clock. After clearing all the security drills, we used to land up at a site in the afternoon. But still, with all these, and also as Sahil brought it out, Methi River, and the labor after getting his background checks, police check, medical, we used to get him on the site, and next day he wouldn't turn up. After going through all the and seeing the site conditions, he never used to turn up for work. Therefore, advanced planning was required. As Gupta sir rightly brought out, there was monetary penalty involved. The aim was without stopping the movement of the aircraft and carry out the structural health validation of Methi River Bridge, which I feel we did it very successfully. We acknowledge the support and guidance extended by all the agencies involved in the project. Now, a point to consider, like my eminent panelists earlier had talked about various bridges, and especially the ROBs and cable stay bridges which have come up with health monitoring system, where real-time parameters are being recorded, and through a signal or a communication where the value, whenever the parameters are breached, the signals are communication is made. However, what I feel is there is a requirement of real-time analysis through cloud computing based real-time finite element analysis of the structures, such that we can work out as to if this load has crossed at this point of time, what will be the effect on the structure. Thereby, what I mean is making a digital twin. And thereafter, this is what I feel should be a future scope for the SHM, getting into the predictive analysis for these structures. With this, we end our presentation. Thank you so much.
Thank you, Lieutenant Colonel Harsha Chatty and Engineer Sahil Matre. Thank you very much. Before our speaker leave, I request Dr. Sanjay, Dr. Suresh Bhallaji. Dr. Suresh Bhalla, can you hear me?
Yes, I can hear you. I have another commitment at 7 o'clock.
Only question is there for you before you.
Okay.
You can also Sri SD Lime sir has given a question. that very informative. How is the data transmitted in the example which was cited of Delhi composite girder span? Does it require separate data acquisition system at site and thereafter transmit to the control analysis center? Is the power generator sufficient for this? Can it generate automatic trigger in case of unsafe situation?
Yeah, that's a very good question. So our computations, they show that the power generation process, it can happen, and the energy can be stored in rechargeable battery. And when the battery is charged, then it can carry out the measurement, it can carry out the data processing and data transmission. So that is very much feasible. And of course, in the next phase, now we are planning to do a full demonstration of this. Here we have demonstrated that yes, the battery can be charged and we can obtain power in the range of say milliwatt. Our next objective is that we do a live demonstration that we are doing a data transmission. I hope I have answered your question.
गोपाल राज जी अनम्यूट कीजिए.
Gopal, please unmute.
बस 10 मिनट.
Yeah, Suresh, Dr. Suresh Bhallaji, there is one query that they are looking for. Can you come up with the bridge monitoring system for a new bridge and the old bridge? What the instrumentation should come, okay, and which is durable like the bridge life or at least for some years. It can be implemented in the bridge also, and it can be implemented into the old and new bridges. Can we derive some system?
In general, there is no single point solution as a basically every structure is unique and every problem is unique. So we cannot say that a single sensor is a universal sensor. So it really depends on the particular type of the structure, particular type of the situation, and what we expect. So that's how we have to choose the particular sensor. So I'm not for a particular qualifying any something as a universal kind of thing.
Okay. I think Engineer Dute, our Director General, will like to speak, and he may ask some the question on the part. Engineer DG Dute, sir. Over to you, sir.
So you have to unmute yourself.
Dute, sir, can you unmute yourself?
Can you hear me?
Yeah,
Yes.
I can hear you, sir. Yes, please, sir.
Yeah. All the four presentations, one from GK Sahu, he made the presentation on different types of sensors and how to fix them and get the data for monitoring. It was a very nice presentation. I got one question: how to replace or repair the damaged or non-functional sensors in the structures, say at the difficult locations like well foundations, etc.
Yes, sir. Actually, if say 25-30% sensor is not working, it means we are not getting good data. That is not the thing. If your 10 sensor out of 100 is working, you can predict the health history of the structure. So that is really good. By putting some sensors, you can predict it anytime. Because at the beginning, when sensors were working properly, you are having some data relatively. If in between, if some left, then also you can have something.
Okay, thank you. Thank you, Dr. Sahu. Regarding the other presentations, Professor Sanjay Chikarmane covered health monitoring work done on railway bridges, which was excellent presentation. And Dr. Suresh Bhalla presented futuristic bridge health monitoring techniques, which are going to be very, very useful useful in the future. And last presentation, it is a case study for the work done at Chhatrapati Shivaji International Terminal, presented by Colonel Harshad Chatti and Engineer Sahil Matre. This is one of the most difficult work carried out by them under difficult situation and very, very limited time and limited space. So this is one of the best example of completing the work in 30 days. So in all the 4 presentations were very interesting, informative and educative. Thanks to all the authors. Thank you very much.
Thank you very much, Dr. DG sir. Dr. Balla, I think we don't have much question, but people have appreciated a lot your presentation. That's the best part. And we need one literature for bridge engineers, like for IAV. Your write up, what is do's and don'ts, and what are the instruments we should use for monitoring, like kind of the technical backup, so that we can publish in our regular the magazines which we have. So we really thank you for your valuable time. Thank you, Professor.
Thank you very much. Thank you, Dr. Gopal Rai, and all the valuable panelists. So it was really very good experience for me to interact with everyone, and I think it's a very good initiative of the Institution of Bridge Engineers, Indian Institution of Bridge Engineers. So I hope more such programs will be there. Thank you very much. I have to take leave because I have a class. So thank you, everyone.
Thank you, sir.
Thank you. Thank you.
Yeah. I think Sanjay Chikarmani, Professor Sanjay Chikarmani left because of he's having some class in the evening, IIT Roorkee. Now let me take the question. Our own favorite engineer GK Sahu ji. Namaskar sir, unmute kijiye. One of the most enthusiastic health monitoring doctor, I will say, engineer GK Sahu ji.
But Gopal Rai is the surgeon.
सर फिलहाल तो सर मॉडरेटर का ड्यूटी निभा रहा हूँ sir, actually sir, the first question which has been raised, I think you have replied also. It is very interesting, like very few people talk below the ground. I have also some like below ground, above ground everyone monitor the things and we can see also. But below ground monitoring, like it's a challenging. Can you comment on that? Because very first question was that.
Yeah, that is really challenging. But by putting, say, we should put that in that question he has asked for corrosion. But if putting says one sensor or 2 sensors in the well foundation, say 10 meter depth, 20 meter depth, you can predict, because you have to assume that okay, at that level, that is the status. So something we have to do to know inside the ground. Otherwise, nobody is Pandit na, or this type of things. So we have to make Pandit that is structure only by putting some sensors. So that is the idea only for instrument.
I think Engineer SD Limay sir is there with us. He has some question. If we can ask directly, or Engineer Ravindra Goyal ji. Can you unmute Ravindra Goyal ji?
Just a minute. Yes. What is the question?
Hello.
What is the question?
The below ground monitoring system.
Actually, it can be done only at the time of the construction. But if something has already been constructed and as the question suggests, there is some issue of corrosion, which is basically a post-construction effect. During the maintenance, he feels there is some issue. I think it's going to be a specialized problem. It has to be seen actually physically, then only somebody can comment. So I would suggest that he has to refer to some proper doctor for that.
If I can add to that, sir, what can be done? There are 2 questions here to answer actually. One is, when you instrument, you'll anyway have redundancy. So if some instrumentation fails, some of the sensors fail, you have backup. That is vital and clear. Nothing has a continuous life, assured life. So you have redundancy built into the number of sensors you put in. and you cleverly, if you cleverly juxtapose your sensors so that you build in the resistance. That is part of the planning of the deployment of the sensors, the type and where you will put them. Now, regarding underground structures, there are two. Say a bridge. We're talking only about bridges. So bridges are foundations. So the most dangerous enemy is cover, and the new IRC guideline is there for assessing that, which I was a convener of. So you can look at the geophysical methods of investigation for bridges, and the methods used to assess and detect scour are clearly outlined there. The other point really being made is about underground. Now, when you put something under the ground, it is difficult to get access at least to the outside because it will be surrounded by earth. So you can maybe go into a well on the inside, but you can't go into a pile if it's a large 3-meter dia pile, which is now becoming commonplace for extradosed bridges, cable stayed bridges, large shafts, shaft type foundations, not piles if you call it. It is difficult to go in. So we pre-instrument them. Whenever you put something underground, you pre-instrument for health monitoring. One of the most reliable would be to put Bragg sensors. Bragg sensors can be used for corrosion, temperature, for various issues, strain measurement. So along with the reinforcement, you put in your Bragg sensors for the full length. And as you were saying, Sausab, at discrete intervals, you can grade them and you can pick up that data and channel analyze them very simply. They can be looked at differentially in that system. They can be looked at absolutely in the system. So you can know whether in that same environment, whether some cables, if they're pre-stressed cables, or some reinforcements, if they're reinforcements, are being particularly affected compared to the rest. Relative and absolute. Any assessment in NDT or structural health monitoring is relative. It is, you have to have a datum, and against that you make an assessment. There is nothing like absolute 100% or absolutely assured values to be realized. That is not there in this kind of system. Okay, for health monitoring system. So this is the issues. So you have various, today you have the piezometric device costs about 2,000 rupees, nothing. It is absolutely nothing. You put 20 into the underground structure and leave them and hope some of them will last. They have shelf lives of 20, 30 years. Onset of corrosion would be in about 15 to 20 years in an underground structure, if at all. At least you pick up the onset, forget the rate. You pick up the onset of corrosion and know you have a problem, you don't have a problem. Okay, so these are the ways you have to look at things. You have to look at it in the whole holistic framework. Underground structures, you have to instrument before you put them into the ground. Anything that is above, like a superstructure of a bridge, you can easily go and see. This is the difference, sir. And scour is actually the thing we didn't talk about today, that is addressed in a different publication of IRC, which you can refer. This is what I want to say, sir.
Can I add to that?
Yes, sir. Please, sir.
You see, what Dr. Harshvardhan said is correct. You have to pre-instrument it, which means your instruments must be placed right in advance. And for Mr. Goyal's interest, we were discussing this aspect in Jammu-Udhampur rail link way back in 95, 98, 97 and all that. So the idea came that let us put in, many of them are open foundations. Some of course are well foundations. Idea came that why not we put load cells in the open foundations below that and monitor it in case they fail, the cells fail or some load cells fail or something happens, a small area only will go away, but rest of the area will still contribute to the transfer of the force. So that's about the open foundations. If it is a pile foundation, if I don't know what is the final conclusion, but in the Mumbai coastal road, they are thinking of, for the large diameter piles, this Osterberg cell. And these O cells are placed into the pile and at different levels and all that. And they give you and keep giving you the readings as to what is the pressure at a particular point, what is the skin friction, what is the end bearing and things like that. And they give you that. These things can be done. But there are always doubts whether to do it or not. Like people say, why put something into the pile? Something else may go wrong. So this field is a bit uncertain at the moment. Maybe.
Yeah, but Vinay, there is a, Vinay, if I can add to that, the Osterberg cell was first used in Worley-Bandra link. We were involved with that. My company customer were involved with that. The first use of Osterberg cells in India. They're still there. I don't know what they're doing with that data, who's getting that data, what's being done with it, but we use that. IRC now has got a new guide, has in IRC 78 in the annexure, you will see the use of Osterberg cell, how to use it, how to get it, and how to separate the skin friction from the end bearing. It's clearly detailed, and that's a new advancement in IRC 78 code, okay, which is available to all. And I want to remind Vinay, you might have forgotten, but I haven't, that Ravindra Goyal, you, me, we were all involved in Jammu Udhampur rail link. You know, bridge 20, 154 meter span was a massive achievement at that time. And as I told Ravindra Goyal at that time, you know, for till 3 years ago, it held the world record for 14 years. For so many years, till 2 years ago. And we never knew it. We never knew it as Indians. The Chinese took it only 2 years ago from us.
Right. So over to Dr. Gopal Rai.
Thank you, sir. Actually, one question to Swapnil. I think when I was looking at this presentation, I was thinking, why can't we, like the construction management, the planning and everything, can be together with the monitoring system at the structural and project management can go and go. Can you think on this aspect also? Engineer
No, I
Swapnil.
think, because whenever we are working on a planning prospect of any project, along with the digitalization what we have done, we always think from the perspective of the process. So definitely this is possible, what you are suggesting. And anyways, in the planning perspective, all design parameters and monitoring parameters and the construction parameters are already being considered if they are in schedule. So definitely it can be looked into, and it is a good suggestion. I feel which can take which can give a good advantage.
Your world is going virtual. Why can't we, in a virtual world, we can mount some sensor on the site and we can feel the distress virtual also? I think.
So that's being done. That's being done. Entire New York Metro has a digital twin today, and the digital twin includes structural health monitoring with ranges and tolerances. The devices are virtually installed in the system as it is. So this whole idea of a digital twin is being used in various projects already all over the world. So I think it's only a matter of time before we catch up also. I don't think it is going to be very far. Maybe in our time, we will see it in the next 10, 20 years. The whole idea is this asset management system with a digital twin has to come into realization in India. Then you can do all your what ifs, whether it's for safety or whether it's for operations, whether it's for change in construction, modification in train times, headways, whatever. The whole digital twin is across all domains, structure, signaling, safety, everything, including maintenance strategies. So you can do that, and it is being done.
साहू सर, एक क्वेश्चन मेरा है कि why we civil engineer, let me precise, a bridge engineer, civil engineer, when it comes to construction chemical, we are silent, we don't know the chemistry. Okay? When it comes to instrumentation and monitoring, we are silent, we don't know the instrumentation. Okay. When we'll try to mingle, the correct word is not mingle, or when we'll try to understand both the subject, so that we grow. I think
that is only possible by attending so many seminar, workshop, etc. Because there is no specialized course for that one. And for civil engineers, we are all believe on applied only. We don't want to go and research. We just want to apply. That is okay. But yes, we should know everything.
Because lot of students has put the message on the YouTube also, here also. Why the instrumentation is never, we don't know the instrumentation word, we only CTM, UTM. That is the heavy machines we have, and further we don't, and that compressive strength and tensile strength. These are only two instruments we know. So I think there is a lacuna in our engineering syllabus also.
There is no any course in even post graduation. We live under graduation, but there is no course in post-graduation also. So that is the problem.
Do you feel now it is a time we should initiate with the course in the post-graduation?
Two subjects should be included. One is concrete technology. You see, there is no course for concrete technology. Then how our structure will be safe? Imagine. And this warning system, instrumentation. Yes, if we can add these two, I think we can save our structures a lot. Because you see, just they have shown one case study. You imagine how many times people have inspected that bridge in that period? Zero. So
Yes.
if that is the status, then how you can assure if this structure will go for 100 years? There is no maintenance. You see, water is leaking. I am telling there should be no interaction between water and structure, and there is pond of water inside the box bladder. So how we can assure? That is the really very big issue with
May I suggest
all the
something?
civil engineers. Yeah.
Yes, sir. Yes, sir. Goyalji. Yes, please.
Actually, we badly need a course in bridge engineering, at least at MTech level,
Yeah,
where
definitely. Yeah,
including
definitely.
technology, including health monitoring, including instrumentation, all these things should be covered. Unless until we make a separate bridge engineering, actually, you see,
Syllabus.
since, since we got independence 1947, there used to be one doctor, MBBS doctor. There used to be one engineer, civil engineer. After that, in MBBS, we have got so many of specializations. Now, so far, so MD dental, we have got. Only for that, we have got a postgraduate doctor. But in civil engineering, he is a basically civil engineer. He can do anything. There is no specialization. He can do the operation of eye. He can do the operation of heart. He can do the operation of kidney. He can do the replacement of the knees also. So this is the unfortunate part. We have not developed the specialization in civil engineering. We should have a specialization, and for that, we have to make efforts at the appropriate level. I am trying my best, but unfortunate part is people just do not want to go into the deep of the engineering. That is the whole problem.
Sir, I will supplement.
Yes,
Even our highway engineers, they don't want to see structures. They don't count structure as anything in road. They are telling in 1 kilometer road, there is only 25-meter length bridge. What is your contribution of structures? That is 975 meter is road only. So your contribution is negligible. So if this is the attitude, how you can set your structure? And they don't know. If one just a hume pipe culvert is not working, your whole road network will not work. So this is really mindset of highway engineers. Highway engineers never go below the bridge and never see what is happening. So we have to actually run one course, that is structural safety audit of bridges. They only talk about road safety audit. They never talk about structural safety audit. So there should be one compulsory course for all the engineers, whether he is highway engineer or a structural engineer. They should be attend that structural safety audit course. You see, we can neglect something in road part, but if structure is going to fail within 20 years, 30 years, then how we can afford that? Say how many $1 billion you can put in repairing and
Railway
renovation work.
engineers,
I think,
railway engineers understand that very well.
mm,
And that is there, but highway engineers, you never
Importance
find.
of the bridge.
More than 1
correct.
lakh bridge we are having.
I
We are,
think this is the topic we'll go and go. I will request our,
definitely.
I will put some question and then I will ask opinion from our president, engineer Vinay Gupta ji. Few questions. I will, with that, then I will hand over to Swapnil. Do you feel, like President Vinay Gupta ji, do you feel that this is a time we should now come up with some course in bridge engineering from IIB? Okay. And we should educate the people at least basics. Whether it is a high time, all expert and should come. Please, sir.
I will tell you my direct experience. I was a part of the board of studies of GVP College at Vizag. And on my recommendation, they started a course on bridges. And that was the elective course, no doubt. So after 1 year, when we met again, I asked them what happened. They said nobody elected course. So I said, that is not the way you have to do. You have to make it compulsory. Now the professors were worried how they will teach because they have to know the engineering first themselves, the bridge engineering. So I said, no, what book you refer, I will tell you. So certain books, I gave them ideas and they would have read the books and some basic knowledge is always there. And they made the course compulsory. And once they made it compulsory, then of course students had to take the course. They had to do it and they did it. After that, when the students really faced problems and the professors could not solve the problems, then I offered, fine, you send those students to Delhi and let them be here for a week and we will give them rest of the things. So we gave them our design notes, we gave them our other things, and we solved their doubts. And they said, now we are perfect, our job is pakka. Because once you've done good engineering, you get a job. So things, I mean, there are a small example, but I'm sure the colleges must have a compulsory course on bridges.
I think GK Sahu sir might be in education committee and all IT professor, I think they left. I think it's a time we should now rethink.
Really? Yeah, yeah.
We should rethink the modern instrumentation. I was sad when somebody has given a WhatsApp to me and on YouTube and message that we only till yesterday, till today, I was knowing two instruments, CTM and UTM. Today we got to know more instruments. So this is something, and this is a ME structures guy are telling. So this is something unfortunate for us. We need to, and I request, yes sir, Vinay Gupta sir.
Gopal, I want to take your leave. My guests have arrived. Who were to come at come now.
I pass on to, yeah, please, sir. I pass on to Swapnil. I think this subject is close to my heart. Swapnil, over to you. Vote of thanks. Please conclude. And, sir, believe me, all the participants, like all YouTube and still watching and they are listening to the discussion. Thank you very much. Swapnil, over to you. Thank you very much.
So thanks, Gopal, and thank you very much. So I'd like to formally propose the vote of thanks. First of all, I would like to thank all the participants for sparing their time for this valuable lectures, and I hope you have learned a lot from this. With the stalwarts presenting their specific case studies, and Gopal has already briefed the cases, and we have seen the pointers from various senior members from the committee and the panelists as well. So I would now like to thanks our speakers for the topic of health monitoring of bridges by various experts like Engineer GK Sahu sir. Thank you very much. Professor Sanjay sir, thank you very much. He has to leave a little bit early for his other commitments. Dr. Suresh Bhalla, Lieutenant Colonel Harshit Reddy, thank you very much for your valuable time and sharing the valuable thoughts with us. Engineer Sahil Matre, I know him for a long time now, so it's great to have you on the as a speaker, and you have really given a very good insight on the topic. So thank you very much for your insight on the subject. So thank you very much for all the speakers, and now I would like to thank our senior members from IIB. Our engineer Atul Bhoge sir, Dr. Harshad Subbarao, who is being always a support to IIB and always present in all the lecture series. Engineer Ravindra Goyal sir, Chief Engineer Railways. And then would like to also thank Engineer P.Y. Manjure, MV Jatkar, who could not join due to some reason. So thank you very much for your support for conducting all these various lecture series. And now I also would like to thank our team member, our first DG for Director General DG Duty, President Vinay Gupta ji, then my colleague Dr. Gopal Rai, and IIB team members Deepika Singh, who works with Intento, Ruhi Agarwal works with DGC, and our IT coordinator Josefa, for your valuable support and making this a great success. So with this closing remarks, I would like to declare officially the session is closed.
थैंक यू स्वप्निल.
Thank you.
फिर से वही शायरी बोल रहा हूँ, ना बोल सकते हैं ना शोर मचा सकते हैं, ना बोल सकते हैं ना शोर कर सकते हैं, मॉनिटरिंग सेंसर लगा दो पुल में तो दुर्घटना से बचा सकते हैं.
बहुत अच्छा. Good.
Concluding. Thank you very much.
Thank you everybody. Thanks a lot.
अरे बंद ही नहीं हो रहा है अभी.